Good morning, Professor Nair.
Yeah, good morning.
Hope you are enjoying sharing your knowledge with our participants.
Yes, very nice. Yes.
Thank you so much.
Okay. So I guess I can start, right?
Yes, sir. Good morning, Professor Nair and all the participants. Welcome to the second day of the SMA workshop. Yesterday, we had 3 enlightening and engrossing sessions on SMA, and we are all very excited to attend today's 3 sessions as well. So over to you, sir.
Yeah, okay. Yeah, good morning, everybody. Welcome to the second day of our workshop. So, we will have again 3 lectures, and we'll cover the rest, let's say, of my presentation slides, and then I will give you some additional information based on the slides you can find on the website. I've given you the address yesterday. So that's not what I want to say. Okay, so yesterday I've told you a lot about the fixed and random effects model of meta-analysis, given different effect sizes, like the mean difference or standardized mean difference for continuous outcomes, the log relative risk, log odds ratio, or probability difference for the binary outcome. You can do now the meta-analysis. And of course, given other effect sizes like the correlation coefficient, the hazard ratio and survival data, when you have a standard error or something about the precision of this estimator, you can apply all the methods we have talked about yesterday. As I told you yesterday, usually we have only the data from published studies. We do not have the original data, and we do not know whether all the studies who are conducted for the topic you are interested in are really published. And of course, there is some kind of risk when you have only the published studies. It could be that your conclusions are a little bit biased because there is a kind of a tendency that many significant results are reported and many non-significant results are not reported. And when you do not have these non-significant results, yeah, so your conclusion is biased in the direction that you will get maybe an overall significant result from meta-analysis, though so in the truth, it's not a significant result. And so the idea now is that we look at some of the methods, how you can really judge what is called the publication bias. there are several methods how you can try to judge it. It's a relatively, let's say, an informal methods, not really like the usual mathematical statistics. You know that maybe you estimate something and you get an standard error, confidence interval, or really a test. In this part here for the publication bias, you apply some methods simply to get an idea, whether publication bias is present or not. Of course, we will have several assumptions, and you do not know whether the assumptions are fulfilled. Yeah, and on the other hand, also we will see that you could do some kind of sensitivity analysis. That simply means that we can, for instance, add some artificial results and look whether these artificial results has an impact on the overall meta-analysis result. For the publication bias, there is also another notion now that is a small study effects. I will use publication bias throughout this lecture. And the idea behind these notion small study effects is that maybe you do first when you have an idea what maybe, for instance, let's say a good treatment is, that you start with a small study and you get a very, very significant effect. And then you say, oh yeah, maybe it's a good treatment. I have to do a larger study. And the larger study maybe also shows an effect, but the effect is not so large as in the small study. And I will explain it, this notion again, when we see one of the plots, then it's easier, I guess, to understand what's going on. So the idea now is that we will discuss several methods how you can try to judge whether publication bias is present or not. And sometimes the simplest methods are not the worst one. So we will start with the fall drawer method, and that's a very nice and simple idea from Rosenthal, 1979. It's a kind of a, what I say, already said, simple qualification based on the summary p-values from meta-analysis. Yesterday, I told you that sometimes only p-values are available, and you can combine these p-values also to get a kind of overall conclusion from meta-analysis. But we haven't discussed these combination methods. Now I will discuss at least one of these combination methods, and this can be used for this file drawer method for publication bias. Assume now that, again, we have k independent studies available for the meta-analysis, and yeah, usually we say leads to, and assume that all these studies really lead to significant results. And what we then can do, that we can combine the p-values, and we assume now that the p-values also leads to a rejection of the overall null hypothesis. And then the question simply is there any set, let's say, Carnot unpublished non-significant results? So when we would include these non-significant results in our analysis, we will reject the null hypothesis. We will not reject the null hypothesis with this k plus the unknown k naught studies. And one method for combining the p-values is the so-called inverse normal method. Again, it's important that from the published studies, you have the exact p-values. So the information p-value less than 0.05 or 0.01 is not sufficient for this method. You have to know the exact p-values. And also it depends more or less first on the continuous distribution for the test statistic. Then you may know that under the null hypothesis, the p-values comes from a uniform distribution. And then you can do some transformation for these, let's say, uniformly distributed p-values in the following form, that when you transform it with the inverse of the cumulative distribution function of the standard normal distribution, and you sum up them, then you have normally distributed values, and you divide it by the square root of k, such that under the null hypothesis, now these combined statistic capital Z is standard normally distributed. So, and what we will do here is usually then given under the null hypothesis that we have these combination statistic capital Z, we would reject the overall null hypothesis if these the statistic is too large, larger than a critical value. And now the assumption of Rosenthal. Assume now that there are k-naught unpublished studies, and the average effect is 0. So it simply means that the p-value is 0.5. Yeah, such that when you do the calculation here with the inverse of the CDF, yeah, the contribution is 0 to the sum. And then simply the question is, how large must be this k-naught, such that when you look now at this statistic here, yeah, the value of the statistic is less than the critical value. And that's the simple idea. That simply means how many unpublished studies do we need, such that instead of the significant result, we will get a non-significant result. Yeah, when you have here this inequality, you can solve this inequality for k-naught, and that would be the solution. Yeah, so that's the simple idea based on the assumption that there is no effect observed in the k unpublished studies, and the p-value is 0.5. Yeah, under this assumption, you can do this method. So, and then you can calculate based on the data you have. When you have the exact p-values, you can calculate this number. Yeah, and then the question is, how do you interpret this number? And of course, it's not easy to give a general rule, but what do you think? So when this k-naught is, let's say, relatively large, I think you do not have to worry about publication bias, because it's not expected that you have a large number of non-published studies for a hypothesis or for a topic leading to non-significant results. Yeah, there will be no sponsors for doing a lot of studies with non-significant results. But when the number of k-naught is relatively small, maybe 2, 3, or 4, and you have 20 studies, maybe then you can worry a little bit about publication bias, and say maybe there are really 2, 3 studies, and we only need these 2, 3 studies such that our significant result will become a non-significant overall result. Yeah. So, but it's just formally, let's say, just a number. Of course, you cannot change your overall conclusion from the meta-analysis, because you do not have the results from the unpublished study. So it's just a number K naught to see a kind of a sensitivity analysis under the assumptions given here. What will happen when you have a significant result, and then you will get a non-significant result when you would have the results from the unpublished study. Yeah, so that's the usual way for this so-called file drawer method, yeah, that you can think about from having a significant result, that you determine the number of studies such that you will get a non-significant result. Yeah, so that's the basic idea. And this method is implemented in the R package Meta4. And so that's a small program here. The function is FSN, fail, save n. And it uses the Rosenthal method with this inverse normal method for combination of the p-values. Yeah, so and here is a simple small program for it. So that is the data set for these vaccination data you have seen yesterday with this tuberculosis. This data set is already given in this Meta4 package called now called it's 1994 because that's the original reference. And maybe you can calculate the log relative risk. Yeah? And here, for instance, again, an example to use the effect size calculation function in this Meta4. Yeah, and then you will get the data set, yeah, where recall yi is the estimate, the log relative risk, and vi is the variance of these estimator. Yeah, and then you can apply these simply to this function fsn, fail, save n, and you will get these result. Yeah, so the observed significant level for the studies given here is very, very small. And of course, you can use different target significant levels. The default value here is 5%. Of course, there are options here in this function that you also can say, wow, I only want 1%. And so that's a very extreme example. What you would need here is nearly 600 studies with no effect, such that the observed significance level is at least larger than the target significance level. Yeah, and of course, yeah, you would never say, okay, I've overseen nearly 600 studies, or there are really 600 non-published studies on the question whether this vaccine is effective or not for tuberculosis. Yeah, so in this situation here, applying the file drawer method, you do not have to worry about publication bias. Of course, there are a lot of other possibilities you can think about how you can extend these file drawer method. Yeah, for instance, let's go back to the slides here. Yeah, you can also say, maybe I will also add, let's say, a very small positive constant, so that instead of p-values of 0.5, you can say have p-values of 0.4. So then you would add a little bit here. Yeah, but there are still some as a constant depending on the number of unpublished studies. Yeah, and you can also then look for the number of k0 with p-values of 0.4, such that instead of the a significant result, you will get a non-significant result. So I also can play a little bit. And I think Dr. Sinha did some work on this. Yeah. So there are some other methods given here, and they are also implemented in these function FSN. So you can use different types. So they, without any type here in this function, the Rosenthal method is the default method. Yeah, so there is also the method by Orwin and the method by Rosenberg. The Orwin method calculates the number of studies averaging null results that would have to be added to the given set of observed outcomes to reduce the unweighted average effect size to a target unweighted average effect size. So that's a little bit another idea that you have your estimate, let's say from the fixed or from the random effects model for your average effect size. Yeah, and then you simply assume or look for the number of data such that the, let's say, new average effect size with these possibly unpublished studies will achieve another value. Yeah, so that's a little bit another idea, that instead of looking at this significance level, that you had a target significance level here in the Rosenthal method, yeah, in the Orwin method, you have simply a target average effect size. The second method here on the slide, the Rosenberg method, calculates the number of studies averaging null results that could have to be added to the given set of observed outcomes to reduce significance values to a weighted average effect size. So it's a simple, similar idea. It's a kind of combination between the Rosenthal and the Orwin method. Yeah, you can also, and then simply the result would be the same. Like here, you will get a number of studies, and you will see what it will be the result, and then you get, when you get a very large number, then of course you don't have to worry about publication bias. If the number is relatively small, maybe you have to worry a little bit about publication bias, and maybe then the consequence would be for the meta-analysis that you do not say, you know, I have really a significant result. Maybe you say, oh yeah, maybe when there are 2 or 3 studies not really published, and when there really exist these non-published studies, maybe then we'll get a non-significant result. So then the question would be, or then you would say that you need some more really published studies, new studies, to confirm your overall significant result or not. So that is the simplest possibility what you can do for judging the publication bias. So the file drawer method is not often used, let's say, in biometry epidemiology, in these, let's say, biomedical literature for meta-analysis. It's more often used in the behavioral sciences and psychology in these areas. So the standard analysis for meta-analysis in the let's say biomedical literature, and that is also what you find on this PRISMA statement I mentioned at the beginning yesterday, is these funnel plot. And here is a little bit the theoretical modification or motivation for the funnel plot. So, and it depends on, let's say, normally distributed variables with known variances. So when you do it and you have independent variables with an identical variance sigma square, and you want to do a confidence interval for the mean, the expected value of these xi's, you would use these confidence intervals. So sample mean plus minus square root of sigma square over n times the critical value of the standard normal distribution. And what you simply see here or have to recognize is, so smaller sigma square is, the smaller is the width of the confidence interval. And the larger this variance is, the wider is the confidence interval. So, and you have here the standard error of the sample mean as a measure of precision. There are other alternatives you can look for or use for kind of precision. So precision is 1 over the standard error, for instance, given in this form. But maybe you can also use n over sigma square or the sample size itself or the square root of the sample size. So there are different possibilities here now that you can use as measures of precision. And of course, everything what you see here as measure of precisions are fixed, and they had nothing to do with the sample mean here. And when you have normally distributed random variables, you know that the estimator of sigma square, the sample variance, is stochastically independent from the mean. And that's a very, very important assumption for the funnel plot, that you have, let's say, an effect size. Now here the sample mean and the measures of precision are stochastically independent of the sample mean when estimates are used. So with the sample size, you do not have any problems. So, and this is the theoretical basic idea of a funnel plot. What's shown here on the x-axis, you have your effect size estimate. And on the y-axis, you have a measure of precision. So, and look that the number of precision, if it is very large, so the important thing here now is that here stands the precision. So in case it would be the standard error, it would be the other way around. Then the smallest weight value would be here at the top. So, and then you simply have your, let's say, mean or estimated effect size. Here it's now 3. And for each of the possible precision, you can determine the confidence interval. And then you draw a line for the lower bounds of the confidence interval and a line for the upper bounds of the confidence interval. And this picture would look like this, and you can say that is kind of a funnel. So, and now what is the idea now of using these funnel plot for meta-analysis? It was first proposed in a paper by Light and Pillemer in 1984. And it's a kind of informal assessment of publication bias by a graphical model. And the idea is the following: if no bias is present, the plot would look like a funnel. So what you do, and we'll see it on the next slide, I guess, is the following, that you do simply a scatter plot. The scatter plot of the effect size and the corresponding values of the precision. And when you do this scatter plot should look like a funnel. That's the idea. Yeah, and of course, the following idea is when there is low precision of the studies, you have a larger variation of the effect size, but the larger the precision is, the less should be the variation of the estimated effect sizes when there is some true effect size. And all the studies have, let's say, an overall average true effect size. Yeah. So, when you have a kind of an asymmetric funnel plot, this may then indicate a possible publication bias. So that was the original idea by Light and Pillerman. And of course, when you look at these funnel plots, here I just have the label precision. Yeah, and when you go back one slide again, there are different measures for the precision you can use. And you will also see in 2 minutes or so that this could affect the graphical presentation. Yeah, and in a paper in 2001, Stern and Egger said that the standard error of the treatment estimates is plotted on the y-axis, which is likely to be the best choice. Yeah. So, and here is now funnel plot. There are a lot of data points here. On the x-axis, we have the relative risk, and on the y-axis, we have the standard error. So recall that the precision is 1 over the standard error. So it's in other order here, the values from in the y-axis. So we always start here with 0. Yeah, and then going down, we increase the standard error. And what's going on here is the lines here stand for the corresponding 95% confidence intervals, and you would have these data points here plotted in the funnel plot. Of course, what you see first is there's only maybe here one study that is outside the corresponding confidence interval when the overall estimate or average effect size is given here. But it doesn't matter. So the only thing is that I want to show you here is that it's not really an asymmetric, there's not really a symmetric funnel plot. Usually you do not have any problems with high precision studies. It's the problem always is with low precision studies, and that's the reason also why this publication bias is also called the small studies effect. What you have here is that you have here some studies with a certain effect less than 1. Yeah, but on the other hand, these studies are here missing. Yeah, so that's the reason why we have here an asymmetric funnel plot and not a symmetric one. We would expect that here also there would be some studies if no publication bias is present. And when you assume now that values less than 1 are in favor for something for the relative risk, you have, and then you get significant results, let's say to the left, and non-significant results to the right of this estimator. Here's some non-significant results may be missing or not. So that's the idea behind the funnel plot. That's simply a graphical method. So I do not have included the different measures here now, but it doesn't matter. So that's the standard recommendation, that you have the standard error on the y-axis. And in the meta-analysis packages, you will always have these standard error on the y-axis. That's simply a graphical method. And of course, when you're doing statistics, maybe you want to have something like a statistical test also, and not only a graphical method. Maybe when we do now here, I will ask everybody of you here, and maybe someone would say, yeah, it's publication bias. Somebody would say no. And of course, it's not easy with a graphical method to get a general conclusion. Maybe when you would have here at least one study in this area, maybe you would say no publication bias is present, or we do not have to worry about publication bias. And so now we get some ideas in the next slides to do statistical tests. And there are two possibilities how you can, let's say, twist this funnel plot. And the test is known as Egger's regression test, and it's the standard test in meta-analysis. And also when you look in this checklist from the Prisma statement, you will also see that you have to judge whether publication bias is given or not. And the classical test often used, or nearly always used, is Egger's regression test. So, and that's the following idea now. You change the role from the funnel plot to this regression model. So on the x-axis here now you have your standard error, and on the y-axis you have your effect sizes. Yeah? So simply you turn it here around. Yeah. So, and the variance of this error is given in this form here. And when there is no publication bias, then it would be that when you fit this regression line, yeah, so the slope parameter would be 0. So that the idea now is when you fit these regression, yeah, and test whether the slope parameter is equal to 0, that is equivalent to the null hypothesis that you do not have publication bias. Yeah, and you would reject the null hypothesis of no publication bias, yeah, if the estimate of the slope parameter is too large. Yeah, so the usual way for testing on regression parameters. Yeah, so I think that was the original version. Now it's a little bit of change in the R packages, that kind of a modification, but it's not. So the reason is that here we have, let's say, a weighted linear regression, usually not a problem. So, and now what when we do is that the variance of the, let's say, error term is equal to 1, we have to divide it here and here by the square root. Yeah, so that, let's say, here on the dependent variable, now we have the effect size divided by the standard error, so some kind of a Z value, a standardized value, and now on the x-axis we would have 1 over the standard error. Yeah, and then when you then would look at the theoretical funnel plot, yeah, you would see that the top of the funnel plot is now identical to 0 as the intercept. Yeah, and that simply means that the null hypothesis, no publication bias, given this model here, is equivalent to the null hypothesis that the intercept is equal to 0. Yeah, and then you can do a test for testing that the intercept is equal to 0. Yeah, so in other words, under the assumption of no publication bias, the plot between the x and the y variable goes to the origin. Yeah. So, and that's a possible, yeah, so that's simply the idea about this EGA test, and that is the standard test you use in meta-analysis now for judging publication bias. So of course there are some, let's say, variants of these regression tests. First of all, when you look again here at this line, a regression equation, we simply assume now that, let's say, we have a fixed effect model. So there is no heterogeneity parameter included here, but you can also say whether we can judge it not under the assumption of a fixed effect model, but also on the assumption of a random effects model. Yeah, so there is a possibility given in this function of the R package meter that we can include an estimate of the heterogeneity parameter in the variance structure. And just to give you an idea. But it's more important here now, the second point. As I've already told you, I've told that the important assumption for the symmetry of the funnel plot is that the estimate of the effect size is stochastically independent from the measure of precision. Of course, this is true for, let's say, the mean and its standard error for the mean difference and its standard error when we have normally distributed data. But recall that yesterday also for the standardized mean difference, we have seen that these estimates, effect size estimate and variance estimate are stochastically dependent. And especially for binary data, there is a dependence between the effect size estimate and the variance estimate of this estimator. And then the effect is that even if there is no publication bias present, the funnel plot is asymmetric. And that's the reason why other tests have been proposed for these funnel plots. And simply the idea is to use now, instead of explanatory variables depending on, let's say, the standard error, that you use something that is independent of the effect size. And of course, one possibility would be given in this paper by Peters, that you simply use the sample sizes. Yeah, so that instead of the precision here or the the standard error, so instead of the standard error, you will simply use the inverse of the sample size, so that the inverse, the usual sample size, is now the measure of precision here. So that's a simple, also a simple idea. Yeah. So, and in a paper by Rücker and co-authors, they simply said use these Arcsine transformed effect size for the binary data. Yeah, so that's the effect size we haven't discussed a lot yesterday. That is this Fisher's variance stabilizing transformation. It's nearly this same argument like in the Peters approach. When you do the Arcsine transformation as a variance stabilizing transformation, the variance just depends on the sample size and nothing else. Yeah, so these methods also implemented in the function meta bias in the R package meter. And you will also get the R package and the R package meta for these tests, the regression test, using the function rec test. Yeah, so, and here is a simple program again with our amlodipine example we have already seen yesterday. So this is nothing new on this slide. So the data set in the two groups, we've calculated the difference of means, calculated the variance estimate. So and then we use the meta-gen function here for this generic inverse variance meta-analysis, and recall that in this meta-gen function, the second argument must be the standard error and not the variance of the estimator. So and when we have our object, Eggers test, let's say, is the default one, and you simply use this function meta bias and apply it to the R object, and then you are done. You think that you are done. Question, of course, is how many studies do we really need? So yesterday we had this question for the meta-analysis, and I've told you that you need 2 studies for meta-analysis. Now we want to fit a regression line, and of course, there is no general answer for this question, how many studies we need now for this regression test. But implemented in this R function is that the minimum number is 10. Unfortunately, we only have here 8 studies in the amlodipine example. But you can change the default number 10 to the number you need. So with this k.mean option, you say that it is 8, and then you will get the results. Alternatively, when you want to include an heterogeneity parameter in your analysis, you have to say that the method is this MM. So, and this is now the result you will see for this Eggers test. So we have with these 8 studies, of course, you can fit the regression line with that 8 studies, and you will get these kind of test result. So it's the test for the intercept, whether it's different from 0 or not. And with the degrees of freedom and the p-values here is, the p-value here is nearly 75%. So based on these analysis here, you do not have to worry about publication bias. Here you also get some information about some sample estimates you have. So, and here again, like it is in the R package meter, you get some information about the implemented test. When you use it with the additive heterogeneity estimator, of course, the overall result would be the same. But here it is a little bit smaller, the p-value. It's nearly 30%. So again, like a kind of recommendation when you do this, we can also always do the sensitivity analysis in different meta-analysis method. Maybe then you can use the Eggers test and the modification here with this heterogeneity parameter included, and see whether there are different conclusions or whether not. And that's here in this case, no problem that we would say here in this small example that there is no no publication bias present. So this is, let's say, the standard part in or standard analysis for the publication bias in the biomedical literature. Another idea I will show you here, what you can do for then now correcting for publication bias, is the trim and fill method. Up to now, we had only methods like the fault draw method and now this graphical method, the funnel plot, and the corresponding regression tests, where we just said yes or no for the publication bias. But we do not change our overall results. And the trim and fill method is now a method that maybe you can try to correct under certain assumptions for publication bias and do the meta-analysis with some, let's say, artificial results. So when you have the notion of publication bias, you can also say that it is selection bias. So it depends whether you look at the whether you publish a study or whether you can use or have the data and maybe then according to several criteria you may select your data or studies for the meta-analysis, and maybe you know that there are some published studies, but these studies do not give you the data you need for meta-analysis. So that simply means that also this testing for publication bias is also a kind of testing for selection bias. And now the idea is here, based on the original paper, using the notion selection bias, now that we want to adjust the treatment effect for selection bias. And also we get an estimate for the number of missing studies. So the basic idea of this trim and fill method is that we add studies to the funnel plot until it becomes symmetric. So we have the strong assumption that the funnel plot should be symmetric. As we have already learned now, that is not always the case. Even if no publication bias is present, the funnel plot in this situation could also be asymmetric. But this is now a very important assumption here for the trim and fill method, that the funnel plot becomes symmetric. So when we do 5 steps, I just give you here the idea, not so many details. So the first one is estimate the number of studies in the outlying part of the funnel plot using rank-based methods. So that's the first, simply the step you do. In the second step, you remove these studies. That's a trim step, and do meta-analysis on the remaining studies. Now that we consider the estimate from the trimmed meta-analysis as the center of the funnel plot. And for each trimmed study, then in the fourth step, we fill an additional study at the mirror image about the center of the funnel plot. So after trimming, we do the meta-analysis of the trimmed of the studies without the trimmed one. So then we get, let's say, a new center for our funnel plot. Then we include our trimmed studies again and fill as a mirror image the studies on the other side. And then we do the meta-analysis on the original and the filled studies. So, and then the question is, of course, we do some meta-analysis here. Should we use the random or fixed effect model? And of course, there are some simulation studies on this part here. So the question I've said is whether we should use a fixed or a random effects model. And the recommendation is that for the first 4 steps, you should use a fixed effect model, and for the final one, a random effects model. So it's just based on several simulation studies. So one important thing here is that we do not consider any explicit mechanism leading to the small study effects, or so to the effect for the selection. Yeah, we do not have any assumption about the mechanism of the publication bias or the selection bias here. Yeah, of course, I've already said that is a strong assumption here that the funnel plot is symmetric. Yeah, and of course, also based on simulation studies, is that when there is substantial heterogeneity given, yeah, so the method is not good. Whatever substantial heterogeneity really means. Of course, that's also then an effect here. What should be obvious, since we include now some studies, that simply means that we do have more information than we really had. So that's a kind of an increase of a statistical power that we will get maybe too narrow confidence intervals for the average treatment effect in our final or adjusted meta-analysis. So that also you have to keep in mind. So, and I've copied this program here on the slides, and I've used the data set here, and there are some, when you're interested, you can look in this explanation. I've just used also a fixed or a given data set from the Meta4 package, Lee 2004. And again, now we use the odds ratio here. And recall that in the Meta4 package, it's always the log odds ratio you will get. Yeah, we can look at a funnel plot simply by applying funnel to the R object. Yeah, and we can simply use the trim and fill function in this Meta4 package by applying to this R object. Yeah, and maybe then we get the summary of this trim and fill method. And also what you can do is the funnel plot, that you can look at the funnel plot now on the trim and fill method, and that's the only one I will show you. The Henry-Koppers approach will be the next one. It's already here on the R program. That will be the last slides for the publication bias I will talk about. And alternatively, you can do, of course, the analysis in the R package meter. So here now, we can use the metabin function, and it's also the trim and fill, and you can do similar, or look at similar analysis here for this method. So first of all, the results for the standard meta-analysis. Again, from the Meta4 package, we have seen yesterday that the default estimator for the heterogeneity parameter in the Meta4 package is the restricted maximum likelihood estimator. In the other package, it's the decimonial layered estimator. So, and we have here a very substantial heterogeneity given. So the p-value for Cochrane's homogeneity test is very small, and we would get these model results. So the overall estimate for the log odds ratio is 0.7, and the confidence intervals are in these parts. So minus, so I've overseen the minus sign here. And the confidence interval is from minus 1.1 to minus 0.3. So we get a very significant result here. And when you use then the trim and fill method, there is a little bit to change, but not so much. So that in this situation here, in this example, you do not have to worry about the publication bias. Yeah, so we will include these studies. You will see it on the next slide, where there is a funnel plot. Yeah, you get also here some criteria for the models. I do not know why it's really important here for the meta-analysis model. So the important thing, first of all, is that here we have the 2. So that's the number of missing studies estimated. And you will see it in the funnel plot on the next slide that is on the right side. And then we do the trim and fill method. Yeah, so recall that first we will trim these 2 studies, do the meta-analysis, have a new center of the funnel plot, add these 2 studies again, and as a mirror image on the other side, we add 2, let's say, artificial studies. Yeah, oops. So, and when you do then the meta-analysis, then the result would look like this. Yeah, for the trim and fill method. Yeah, so the estimate here is a little bit shifted to 0. Yeah, also the confidence interval is a little bit shifted to 0 compared to the results here. Yeah, but still we have a very significant result for the overall conclusion here. So yeah, with the trim and fill method, there is nearly, let's say, the same result. So what happened? So it's on the other side here. Yeah, and this is now the result of the funnel plot in the Meta4 package. Yeah? So in different R packages, there are different, let's say, displays. So the bullets here are the original studies. And again, you have here the estimate and the corresponding 95% confidence intervals. Yeah, and the y-axis again, the standard error from the top to increasing to the bottom. Yeah, so and what has happened now is from the method, yeah, this and this study, they were trimmed. Yeah, so they said these 2 studies, yeah, when we trim these 2 studies, we had a symmetric funnel plot. So based on the data here, we get the new estimate for the center. Then we include these 2 studies. Yeah, so that is now outside this area. It has not any meaning. Yeah, because it's shifted to the right and after the trim step. Yeah, and then we have the mirror images. So for this study here, we have an artificial study here. That's a circle. And for this study here, we have an artificial study result here. Yeah, this is the circle. Yeah, and this is now the symmetric funnel plot. And then we do the meta-analysis. So once we do the meta-analysis without the 2 circle studies here, and after trim and fill, we do the meta-analysis, including these 2 artificial results. Yeah, and then we can compare it. Yeah, whether there is a big difference or not. In our example, it is not really a big difference. So one comment, if you use the other R package meter, I think for this example, it's not really clear what is going on in the first step here with this rank-based method. So when you use these function or the trim and fill method for the same data set, it could be that the number of studies or in the outlying part are not the same. It could be, for instance, here in this example, in the meta package, when you use these R code here, you will see that here 3 studies were trimmed after the first step. Yeah. So, and finally in this lecture, I just want to give you the idea of the Henry-Koppers approach. Yeah, recall that we have already seen the function HC in the R package metaphor for do these approach. So recall from yesterday that I've shown you that when you use the random effects model, instead of the fixed effects model, the weights in the random effects model are more equal than in the fixed effects model. That means that studies with a high precision in the fixed effects model has a smaller precision in the random effects model because of the weight. And of course you can say, I do not want the random effects estimator. At least for the estimator, I want to stay with the fixed effect meta-analysis estimator. Yeah, so, and it simply means we only use the within study variances as weights. Yeah, so because then you have the original, let's say, precision of the studies on just the precision. You do not have any model assumption. Yeah, like the random effects model. Yeah, that there is an additional parameter. And but then you will do the following. Yeah, we calculate the variance of the estimator from the first step here under the random effects meta-analysis model. Yeah, so also recall that the when you do it, then in the random effects model, that the confidence interval from the random effects model is always wider than the confidence interval for the fixed effect model. And this Henry-Koppers approach can be, let's say, motivated by simply a kind of a mixture of these two approaches. Yeah, we will stay with the fixed effect model, with the fixed effect estimator. Yeah, but then we want, let's say, to widen our confidence interval for these estimator. Yeah, and when you do have calculated the variance here, yeah, you can try to construct a confidence interval for the parameter estimate. Yeah, and the idea now is that it should be, in some sense, robust to publication bias. So in the idea now that you get a wider confidence interval with this approach compared to the confidence interval of the fixed effect model. So that's simply the idea behind this Henry-Koppers approach. Yeah, so, and this is simply what's going on in this example here. Again, this Lee data set where I have given you some of the information in some of the R package. Yeah, so when you do this here, yeah, so the measure is again the log odds ratio, and you will get these results here, and that is what we have already seen before we look at the trim and fill method. And now when you use the Henry-Koppers approach, then there will be the change in these hoops in these directions. Sometimes it's not really obvious to me why the authors of the R packages changed their default. So when you apply this Henry-Koppers approach, the default estimator for the heterogeneity parameter is now not restricted maximum likelihood, but the decimonial Laird estimator. Yeah, and what you get here is that not really identical, but there's no so much difference between this. Yeah, but the estimate here is now shifted a little bit towards towards 0. Standard estimator is a little bit larger. Yeah, so that's also clear because we use here also again the random effects approach. Yeah, so not so different. And finally, you will get a confidence interval in this direction. Yeah, so and you will see that the upper bound here is relatively close to, let's say, relatively close to 0, but still we have with this Henry-Koppers approach still a significant result to the 5% type 1 error. Yeah. So, and when you want to have the results on the original scale, yeah, in this function, you can use these options transf, yeah, equals to exp, yeah, and you will see that this part here, yeah, and this part here will be transformed to the odds ratio scale. Yeah, and of course, yeah, these is still on the original scale, and the standard error, of course, are not available in this kind of transformation. So this is the basic, well, these are the basics or basic ideas I wanted to show you for the meta-analysis, for judging the publication bias. When you look in the different, or at least in the meta package, there is also something about the Koppers method. Koppers is working very intensively on publication bias. Yeah, so you could do a little bit more also on more elaborated methods like selection models that you really use a kind of mechanism to the selection bias or to the selection, yeah, and do a lot of sensitivity analysis here. But I do not want to show it in this workshop here. So maybe one final comment before we can discuss this, if you like. Here, just for the metaphor package, when you apply the meta-analysis, that is this function RMA. And what you see here is that you do not have to use the effect size calculation function before. Yeah, you can use these options for the 2x2 tables directly in as the arguments here in the RMA function. Yeah, so it is not always necessary first to use the effect size calculation function and then the RMA function in the R package metaphor. Yeah, in most cases you can directly use the RMA function because there are a lot of options the same or arguments which are nearly the same as in the effect size calculation function. So that is what I wanted to present you here in the first lecture. So are there any comments, questions?
Thank you so much, sir. So we are open to questions now. Participants can unmute themselves and ask questions if they have any, or they can also use chat to write their questions. You can unmute yourself and ask questions, please. By the time, sir, we receive any question, so there is a comment by Evie Thomas. Is saying, enjoyed the session, learned a lot of new stuff. And
oh, thank you very much.
And I had one small question, sir. So do the R packages have the option to include HKSJ estimate instead of DL estimate of variance in error test?
Good question. So once again, please. So in the agar test, what do you want to include?
No, there are HKSJ estimate of variance instead of DL estimate.
Ah. Very good question. Never thought about it. I've never. So Dr. Sinha invited me to a talk on publication bias at the end of October. I will think about your question.
Thank you, sir.
Yeah. So very good. Yeah. So sometimes it's good to have such workshops. I never thought about it because I haven't worked so a lot of on publication bias. So I started on a little bit on working now. But a very nice, very good question. I will think about it.
Thank you so much, sir.
Yeah.
There is another question by Dr. and Radha Rajkaur. She is asking, can the Henry-Copus approach be used for binary data as well?
Sure. So it was an example for binary data, Henry-Copus, right? Oops. No, we have already in the, oops, already the meta regression part. Yeah. So this is, you can use it for every effect size we have discussed. No problem. Yeah. So in this example here is for the odds ratio or a log odds ratio. It's for binary. It's no problem. You can use the Henry-Copus approach for all methods we have discussed yesterday.
Thank you, sir. So I can see one raised hand. Just Renu, please, you can unmute yourself and ask your question. Renu, you had raised your hand. If you have any question, please unmute yourself. You can ask the question. Okay, so there is another question by Dr. Neha Midha. She is asking, why is there publication bias against null effects?
It's simply an assumption that when you try to judge whether a publication bias is present or not, you have to do some assumptions. That's simply the idea behind it. Yeah. So, for instance, in the file drawer method, it's just the assumption of a null effect because the calculation is easier. So that's simply the reason. Yeah, when you I know that Dr. Sinha and the PhD student, they did some other effects for the null effect, not really a null effect, yeah, but something different than. Yeah, so the idea for the null effect simply is when you add some studies with a null effect here in the sum, yeah, the only thing is that instead of K, yeah, you would have K plus K naught, yeah, but all the results simply here from the transformation are 0 when you have a p-value of 0.5, so that is a null effect. Yeah, so and when you have something different from a null effect, yeah, so for instance, you can also say that, yeah, no problem that you can say that maybe it's 0.3 or something like that. Yeah, then you would add something here in the sum. Yeah, then you would have, let's say, K naught plus K naught, yeah, inverse of 0.3. Yeah, so that you have an additional constant here. But it's no problem to do the calculation from here to here with this K naught. It's not so an easy formula like here. It's a little bit more complicated. Yeah, but of course you can relax in certain sense these assumption that you do it for null results. It's no problem. It's no a little bit mathematically, it's a little bit more complicated.
Thank you very much. Any other question? Some messages are being written on chat box, appreciating the session. Okay, so I think we don't have any more questions for this session. So we can go on for the lunch break.
Mm-hmm.
And we can meet again at 1:30 IST for the next session.
Okay.
Thank you very much, sir. It was indeed a very enriching session.
Yeah, thank you.
Welcome back, everybody. The last session was also very nice. So I think we can start with the fifth session. Professor Knapp, please continue.
Okay.
Thank you.
So let me see. So this is the part of, or the last part of, let's say, the basic meta-analysis you have to, let's say, learn or have to hear. When we are done with this meta-regression for the rest of today, I will give you some outlook to a little bit more advanced meta-analysis techniques or applications. So what we have done is up to now that we know how to combine the results in the fixed and the random effects model. We are able now to judge a little bit about publication bias. And so the last thing one has to do at least is to explain heterogeneity when you are using a random effects model, and this heterogeneity is quite large. We do this in a technique called meta-regression. In case that substantial heterogeneity is present, possible causes of heterogeneity should be explored. When we would have original data, then you can use covariates on the subject level. Here we only have the data from the published from publications in literature, and we cannot use subject level covariates. We do not have any idea about for instance, the age of each of the subjects in the study. So we only can use covariates on the study level. And of course, we can only use the studies in the meta-regression, which give you the information about the study level covariates. So it could be a scenario that maybe you do a meta-analysis with 10 studies with a substantial heterogeneity, and you have the idea what is the cause of this substantial heterogeneity, and you're interested in several covariates, and but not all the studies report these covariates. So it could be that in the so-called meta-regression model, you could have less studies than in your original meta-analysis. On the other hand, also looking at this bullet here, when you look at the regression model and you have several covariates, if you have too many covariates, there's clearly a great danger of overfitting. And in meta-analysis, sometimes we only have 5-10 studies. And there is it's a rule of thumb from one of a paper I know that the author said that for 10 studies, one covariate. So that means for 20 studies, you can use 20 covariates, and for 20 studies, you can use 2 covariates, and so on. So usually we have only room for a few explanatory variables in our regression analysis. Of course, there are some other problems that you can have, like the aggregation bias. So it does not make sense to really use, for instance, the mean age
as a covariate because you do not have or cannot incorporate the information about the variability of age. Yeah, it could be that you have a study with a mean age, for instance, of 50 years in one study and also in the other study, but the variability of the age in the studies are different. So, and also there is some kind, the problem of confounding as usual in regression analysis, so that there is some kind of correlation between study characteristics, and you should avoid these confounding. So, and of course, there is a clear danger of misleading conclusions if p-values from multiple regression analysis are, let's say here, interpreted naively. The important thing is when you have some study level covariates, which might explain the heterogeneity, you should have a good explanation why it is the case that you have a good explanation for the heterogeneity. So, and the classical example you find in the literature you have seen already is this meta-analysis on 13 trials on the prevention of tuberculosis using these BCG vaccine. As we have already seen, the information we have in the vaccinated and the non-vaccinated group, the number of diseases and non-diseases. And we will see on the next slide in a forest plot that there is a lot of heterogeneity present here when we use the log relative risk or the log odds ratio as effect sizes. And we have to explain these heterogeneity. And the classical covariate used in this example for explaining heterogeneity is latitude. So simply the indicator of a place where the study was conducted, how far it was away from the equator. Other covariates available for this data set is the year of publication. So sometimes there is a trend over time. Maybe the year of publication is a good indicator for the trend over time. In these studies here with the vaccination, there were different type of allocations. So in one of the studies, it was simply alternate. Yeah, so vaccine, non-vaccine, vaccine, non-vaccine. Yes, there was in other studies a random allocation. And the third type was that there was a systematic allocation. Yeah, for instance, village A, vaccine, village B, non-vaccine, and so on. And these are possible covariates that can be used for explaining heterogeneity. All three covariates, latitude, year of publication, and type of publications are all covariates on the study level. And also these are three covariates you usually know from the literature. Yeah, so the year of publications, no problem. When you describe your study, you will also say what kind of type of allocation you have used. And there will also be a description where the study has taken place. So, and this is also kind of an old style of an forest plot, but it's nice to see the problems here or the heterogeneity. So again, we have here for each of the studies the confidence intervals, and in the middle we have the point estimates, and the larger the square, the more precise is the study. And when you look at these forest plot, you will see that there are several studies with confidence intervals which do not overlap. Yeah, for instance, when you look at the study 10 here and you look at the study 8, yeah, so that's the Indian study, yeah, the confidence intervals do not overlap. And that simply means, in a certain sense, so these are the interval, yeah, let's say based on the data, the possible values for the relative risk, and they have nothing to do with the possible values here for the Indian study. And there are several other studies like here 2 and 4, also not overlapping confidence intervals to the Indian study. But there, you can find some more examples where there is no overlap. But nevertheless, given the data here, you can do the meta-analysis in a random effects model like I showed you yesterday. So no problem. But now then you get a significant result in favor of the vaccination so that it reduces the number of tuberculosis. And but on the other hand, when you look at the largest study here from India, there is no significant results. So there is even no difference. So here's a very small study with the difference or the relative risk in the wrong direction. In all the other studies, it at least in the, let's say, right direction, that all the studies at least indicate that there is a favor for the vaccination. So, and now we want to try to explain this heterogeneity. So, and the data information we have is given here by the estimates and the standard errors and possible covariates like latitude, year of publication, and type of allocation. So that you can model in the meta-regression part. I also use here as a kind of motivation this normal hierarchical model we have seen already yesterday as motivation for the random effects model. And the idea is, again, the following. We have our observational model that our estimate theta I had comes at least from a normally distribution with theta I as the true mean in the I study. And we have here the estimate of the variance of our estimator treated as fixed and known. So, and in the first step here, and the structural model, so there use this index here, MA for meta-analysis. We have assumed yesterday that the estimate that the true mean theta I, the true effect sizes, comes from a normal distribution. Now with the average effect size theta, now MI, and the heterogeneity parameter tau square. Alternatively, now what we can do is to explain heterogeneity that we use another, in this situation here, a simple linear regression for the expected value of our true effect sizes. So we say that theta I comes from a normal distribution with an intercept and slope times a covariate. And important thing is that we still have, of course, a variability here. And this tau square with the index now MR is usually called the residual heterogeneity. So, and what is the goal here for explaining some kind of heterogeneity with respect to the expected value? You can compare these two heterogeneity parameters. And of course, if you have a good explanation for the heterogeneity by your covariate xi, then the residual variability or the residual heterogeneity tau square MR should be smaller than the heterogeneity from the classical meta-analysis. So the random effects meta-analysis model is then given in this form when you we have already seen this yesterday when you use the marginal distribution of this normal hierarchical model. We have the average effect size, theta MA, and the between study variability and heterogeneity parameter, tau square MI. Yeah, and when we do the same with this normal hierarchical model where we have this regression part for the expected value, we end up with this random effects meta regression model. Yeah, so and here are kind of an interpretation of the parameters. So the theta MR is the effect size, given that the covariate is 0. Beta is the usual interpretation for a slope parameter. That's the average change in the effect size when the covariate increases by 1 unit. Yeah, and this tau MR is the residual heterogeneity. Yeah, so of course, when tau square MR would be equal to 0, then we would have the fixed effect meta-regression model. And as I have already said, the covariate must have a meaningful interpretation for the issue, and the target simply is that we find good covariates with a meaningful interpretation such that the residual heterogeneity is smaller than the heterogeneity in the meta-analysis. So what you have to do here is simply then for estimating the parameters that you do weighted least square regression because of the different variances you have here. Yeah, so what you want to do is first, you have to decide maybe whether it's a fixed or random effects meta-regression model, so that you want to have a test for tau square MR equals to 0, so that the residual heterogeneity is equal to 0. You can simply use an extension of Cochrane's Q, yeah, because everything we have seen yesterday is based on weights, and you can simply use the weights from yesterday just for doing the analysis here in the random effects regression model. Yeah, you want to have some estimates and confidence intervals for this residual heterogeneity parameter, as well as estimates and confidence intervals for the fixed parameters here in this regression part, the intercept and slope parameter. Yeah, and you can borrow a lot of ideas from the classical standard meta-analysis, from the methods, and you can simply extend these methods for meta-regression. Yeah, so you can use restricted maximum likelihood estimation, for instance, for the residual heterogeneity. You can use all the methods of moments estimator, for instance, that is the decimally layered estimator. Yeah, and what we simply do is weighted least squares regression for the fixed effects. Yeah, so, and of course, I only show here you the examples with one covariate. If you have a lot of studies and you can incorporate more than one covariate of in your model, all the methods can be easily extended to the case of more than one covariate. Yeah, so no problem. Yeah, so weighted least squares regression. So that's the keyword here. Yeah, so here are some slides for some formulas. I will just briefly discuss it with you. There is again a paper. I was the first author at this paper this time, where we extended our 2001 papers to the from meta-analysis to the meta-regression case. And these are simply the formulas here for the extension. So finally, it's given here that in contrast to the, let's say, classical standard confidence intervals you get from weighted least squares regression, we propose again a different standard error for the estimates of the fixed effects. Yeah, and we use again the t distribution and the critical values of the t distributions, and not the asymptotic results with the critical values from the standard normal distribution. Yeah, so and the degrees of freedom here is always number of studies k minus number of parameters in your regression model. Yeah, so when we have only one covariate, we have theta MR and beta, two covariates, so that the degrees of freedom are here k minus 2. Yeah, and there is again what we have shown in this paper with some simulation studies, that the coverage probability of these intervals are better than the coverage probabilities of the standard weighted least squares regression confidence intervals. So, and when we apply now all the different methods for the example of the vaccination for tuberculosis, and just show you here the result for the slope parameter, because this is of interest here, whether the latitude has an effect on the log relative risk for the tuberculosis successor, for the tuberculosis disease or not. And as you see that, yeah, the same names for the methods of estimating of tau square that you have already seen in this standard meta-analysis. Yeah, all these methods can be easily extended to the case of the meta-regression model, and that's the reason why all in the R packages also you can use the same abbreviation like HS for Hunter-Schmidt and DSL for Desimonia Laird. So there's nothing new in the R packages. So what you see here is are the different estimates given the method for tau square you have used for estimation. Yeah, and the results are negative. So the estimates are negative. That means that there is at least they are in favor for the vaccination, that it may reduce tuberculosis, that you get the infection for tuberculosis. When you look at the classical approach, so with the weighted least squares approach and the Z critical value, you will see again also that there is some variability depending on the methods for estimating the residual heterogeneity, as we have already seen yesterday. But the conclusion from all the intervals is the same, yeah, so that they have a good effect so that there is a difference between the places where these studies have been conducted. Yeah, so my interpretation of the estimate here was not really correct. Yeah, so it was a slope and not the intercept, sorry. Yeah, so for the intercept is that, yeah, so we reduce, yeah, so the relative risk, so it's better the farther away are you from the equator. So sorry, that's the correct interpretation here. And when you look at the Knapp-Hartung approach for the confidence intervals, again, a little bit more robust the results, but you will get the same conclusion, yeah, so that the slope parameter is different from 0. Yeah, so and you also could use as an alternative, as I've told you yesterday, this one-step approach. And when you use it in this RMAJ-LLM function in the R package metaphor, with the exact likelihood I was not successful, in the approximate likelihood, yeah, you get some results, and the results are comparable to the results from the two-step approach. Yeah, so why is now the slope parameter negative, and why is it significantly different from 0 when you fit it. That simply means that when you go back to the model, maybe it's easier to see. Yeah, so we have here an intercept, and now it changes with a negative value of beta with respect to the covariate. Small values for the relative risks are in favor of the tuberculosis, are in favor of the vaccination. So that simply means the vaccination is more effective the farther away you are from the equator. So, and this also has a biological interpretation. Yeah, people like you living closer to the equator have a higher natural immunity against tuberculosis than people like me living farther away from the equator. Because one has this nice interpretation for the latitude, this example is always used when you talk about meta-regression. Another thing I want to discuss here is what is really the reduction you have. Originally, they used the decimonial layered estimator. And when you estimate the heterogeneity parameter with the decimonial layered estimator for the log relative risk, it's 0.3, and it reduces to 0.06, the estimate of the residual heterogeneity when you apply this latitude as a covariate in meta-regression. Yeah, and you had really a reduction of 90%, of 80%. And that was also a reason that they said, wow, it's a good explanation because the reduction in heterogeneity is so large. But the interpretation, as usual in meta-analysis, always depends on the method you use. Maybe when you take the Mandel-Powell or Powell-Mandel estimator, that it was beside the restricted maximum likelihood estimator, the one recommended to use in random effects meta-analysis, you only have a reduction of 55%. But nevertheless, in all the cases, we have a reduction of at least 1/3 in the estimation for the residual heterogeneity compared to the heterogeneity in standard meta-analysis. Yeah. So, and how do you do the meta-analysis, meta-regression in the programs? Here, I just want, before I give you a larger R program and discuss it with you, the idea also of the categorical covariate, which is also very important that you do the correct interpretation. That's again this data set with the vaccination data. We use the log relative risk in this effect size calculation function. And in the R package meta 4, you can use the RMA function. So that's the same function as for standard meta-analysis. And the author, Wolfgang Fichtbauer, he's originally a psychologist. And I've learned that in psychology, the covariates are called moderator. So that after these mods state options for moderators, in the way you use the model writing in R, you have to say what are the explanatory variables here. And recall that for the allocation, we had 3 levels: alternate, random, and systematic, and it should be a factor. So that's important. So then you can use the restricted maximum likelihood estimator, for instance, for estimating tau square. You can also omit it because that's the default method. Yeah, and then there is also the possibility to test not only the complete model, the whole model, or complete model, not only the parameters, yeah, also that you can test something like beta 1 equals beta 2 equals to 0. And that will be done here with this BTT C23. And I will explain it, what this means when we see the results. So, and that is what is given in the first part here. So there are 2 slides for this, I guess. Yeah, 2 slides for the output here. We have 13 studies. The estimator for the restricted maximum likelihood estimator is given in this form here. Yeah, and we have here Cochrane's Q. Yeah, and then we have simply a test of the moderators. That simply means that we have these 3 levels of the type of allocation. And the null hypothesis we are testing here is that there is no difference between the type of allocation. Yeah, and that can you test, yeah, when you say these, that you want to use the second and the third moderator. Because what happens when you use these factor with this allocation, I hope maybe they are familiar with this, what has happened, that you have a kind of coding. So one level is set equals to 0, and then you have the difference between the level set equals to 0. So these are the model results. So this is the intercept. So, and this is not really the random estimate for the allocation. Yeah, what you see here is alternate is missing. Yeah, so that here it stands that there's a difference between random or alternate. What is the estimate in the regression model? Yeah, and for systematic, it's not the estimate for systematic, it's the difference systematic minus alternate. Yeah, and what we do here with the test of the moderators is that we test, yeah, whether the differences here, random minus alternative, systematic minus alternative, are identical and equal to 0. Yeah, and you see here, for instance, from the p-values, yeah, that individually there is no difference between random and alternate. There is no difference between systematic and alternate. Yeah, and there is also no difference here then between random and systematic. Yeah, so is what you can conclude from this test here. So, and before I show you a larger R program at the end for this meta regression, some comments here for further applications of the meta regression model. So I've already said that the methods can be easily extended to more than one covariate, no problem. Meta regression is primarily used for explaining heterogeneity between study results. The techniques, however, can be used for also other applications of combining results. So for instance, what you can do is sometimes that you have controlled trials and you also have uncontrolled trials. And you can model it in a regression model, in the sense maybe that you have indicator variables, whether it's controlled or not controlled. And you can use the meta regression techniques I've shown you just also to combine the results from controlled and uncontrolled trial. Yeah, so that means that maybe you have controlled trials, experimental versus control the results. Yeah, you have to have these results separately for the experimental and the control group. So like in the, you cannot have the data like in the secondhand smoking example, that you have the relative risk. Yeah, so how you must have the data results separately for the experimental and the control group. And then you have some uncontrolled studies. Maybe you have only the results of experimental studies, or you have only results of the studies as a control group. Yeah, and then you can combine the results using meta-regression techniques. Yeah, and also what you can do is subgroup analysis, like a little bit indicated already in this covariates example, that you can do the analysis, yeah, only for the random, or studies with the random allocation, for alternate allocations, systematic allocations, and so on. Yeah, and of course, then when building these subgroup analysis, yeah, you can do some. You have to do some assumptions whether you assume a common heterogeneity variance in all the subgroups, yeah, or the subgroups have different heterogeneity parameters. So there is again several possibilities how you can fit these subgroup analysis. So finally, here one program in R for the analysis using these BCG data set again. So I will use the R package meter and the R package meter 4 to show you what will happen in the different packages. So when you recall, we only had the number of diseases and the number of non-diseases given in this data set. Yeah, for the analysis, for instance, in the meta-bin, we need the events and the total sample sizes. So first of all, we have to calculate the total sample sizes for the experimental and the control group in this data set. Yeah, and then you can, for instance, simply do the meta-analysis. So I've chosen again the log relative risk in this meta-bin, using this meta-bin functions in the R package meter, yeah, where you said this is the number of events, the total sample sizes, and so on. Yeah, we can look at the summary. So I also have as a forest plot. When you want to do a subgroup analysis, it's easily done when you're also using this update function, just doing it not to that you do not have to, let's say, write everything again. Yeah, you can use the object, do the update, and just change one of the options, or add some of the options here. And the subgroup analysis is done with this byvar options, and you would say the allocation. The standard method is again the weighted least squares regression method. When you want to use the now Knapp-Hartung for the meta-regression, you can set the options HAKN equal to true, and then you will get the Hartung or Knapp-Hartung results. Yeah, and standard or default, you have here different variances in the groups. Yeah, subgroup analysis. What you can also do is that you can say that the heterogeneity parameter is equal in all the subgroups. Yeah, so, and a little bit more important here too is that our method, of course, is also possible and available for subgroup analysis, not only for the meta-regression part. Yeah. So, and with this, in this part, you can also use the meta-reg function in from the meta4 package, yeah, and then you can do the meta regression. So that simply is then when you have the kind of object here, and you simply say that you use here, and that's a different, or it's different from the IMA function in meta4. Yeah, in meta we have an own function meta-reg for the meta regression. Yeah, so to be precise once again, yeah, so here is a difference. You use different functions for subgroup analysis and meta regression in the R package meta. In the meta4 package, it's not the case. You can use the subgroup analysis and the meta regression in one case or in one function. Yeah, and here is simply that as a second argument, you have to say what is the a covariate or the moderator. Yeah, and also you can do it with the Knapp-Hartung approach. Yeah, so when you have two variates, so that is the simple formula here only for one covariate. When you have more than one covariate, you must use this formula way, the usual way what you do in R when you fit models. Yeah, so, and here are now some of the results only now for the meta regression from the meta-reg program. So just the part here on the second slide. Yeah, and what you see is that is not the style of the meta package. Yeah, because it's a wrapper function from the R package meta4, and the design is of course the result, everything or the output display from the meta4 package. And the important thing here is that the absolute latitude has a significant effect in these model. Yeah. So, and here was a little bit change. Yeah, we have used the allocation now here, and the option for the Hartung-Knapp approach is true. Yeah, so you will get here the result with this Hartung-Knapp approach. Yeah, so, and this, everything is very nice in both of the R packages. But when you compare a little bit the output, I prefer just, especially for giving in so workshops, lectures, the package meta, because you get some more informations in the output at the end. So we use the inverse variance method, we use the Hartung-Knapp approach, and so on. Yeah, when you use the meta4 package, you do not get the information. Yeah, it should be, you have to look at what you have specified, and then you have to interpret the results given here with the R code you have used. And I would, so I like the other way. When you get also some information in the output about the methods we have used. Yeah. So, and these are the results again for two now results. So even when we include the allocation, yeah, the absolute latitude is still significantly different from 0. Yeah. So, and then you also can play a little bit with these moderators. Yeah. So here it's 2 to 4. Yeah. So there is simply the null hypothesis that the parameters of all these 3 covariates are equal to 0. And because of the latitude yeah, we get here the significant result as expected. Yeah, so so that was the regression part I wanted to show you. Here, though, that you have the idea that you use some covariates for explanation of the heterogeneity, and it's important that you use that you can only use study level covariate usually in meta-analysis because you do not have the individual participant data. And the important thing is that you have to use some covariates which has some meaningful interpretation in your subject, in your topic. What are you interested in? Yeah, and here again, it was the latitude, a good explanation why there is a difference in the effectiveness of the vaccination. So this was my part of the basic meta-analysis. So the last slide here of the presentation is, of course, yeah, let's say more meta-analysis. So that's a book already mentioned yesterday. I was co-authored with Joachim Hartung and Picassina. Of course, it's nowadays a relatively old book, 2008, and it's more on the theoretical part. And now there is a new handbook of meta-analysis published last year by Schmid, Stein, and White as editors by Chapman and Hall. And you can see there, let's say, a lot of methods, additional things on meta-analysis you can find there. So this was my part on the regression, meta-regression. So maybe we can do some questions and answers, if you like, at this point before I continue with some advanced.
Thank you, sir. So if any participant has any question at this time, please go on. You can unmute yourself and ask question.
Hello, sir. This is
Hello.
Parmeet, research scholar in Department of Statistics. Sir, I have a question. Like when we do machine learning, what we do is we divide the data set into two parts, like training data set and test data set.
Mm-hmm.
So we, in machine learning, we divide the data set in two parts, training data set and test data set.
Mm-hmm.
So we build the model and test it on the test data set. So can we use that data from this meta-analysis? Like instead of dividing that data set?
No. You normally, in the situation when you only have the published result, it's impossible. Of course, when you would have individual participant data, then you could do it. But of course, you have to think about it. What do you do in machine learning with the tests and the validation data, or learning and validation data set, that you try to build a model, and when you want to see whether it's a good model or not. And now here in the meta regression case, so the observations are here only the studies when you have published data. So sometimes you only have 20, when you have 20 studies, you are lucky. Yeah, and then it's not the idea of building a good model for, it's not so really that you want to predict or something like that with this meta-analysis model. Yeah, you just want to do some, let's say, do some explanation of heterogeneity, whether you can find a reason for this, or when you think about the controlled and non-controlled trials, that you want to incorporate different type of studies in one meta-analysis. So the idea of the machine learning does not really work in meta-analysis. So one possibility, a little bit maybe related to these, not really related, but to the machine learning, is maybe then you can, if you would have some clusters for the studies, then maybe you can think about some methods using mixture of distributions or something like that. But this classical idea of machine learning is not applicable for meta-analysis.
Okay, thank you, sir.
You're welcome.
Any other question, anyone?
Yes, sir, I have one question. I am Dr. Latpade from Pune University. Dr. Latpade, am I audible, sir?
No, you're actually not clearly audible. Can you come closer to the mic or speak louder?
Right now, sir? Hello?
Yes, it's better now. Please ask your question.
Okay. Sir, for the normal setup, this kind of modeling is possible. But my question is that whenever data follows instead of normal, skew normal data is there, is it possible to analyze this data or combine the multiple studies in the context of this meta-analysis?
Yeah, so the important thing is you always have to think about that you do not have the original data. And it's simply what I've just indicated. There are some possibilities to do the meta-analysis assuming different other assumptions than the normal distribution. That's okay. Yeah, it's again the question of what we have with the null results for the population bias. It's here that we simply use the normal distribution just because it's easier or the calculation, but it's still possible. Yeah, when I go back maybe to one of these slides here. So where's my hierarchical modeling? Yeah, so here for this hierarchical modeling, yeah, that you may be either in the meta-analysis model or in the meta-regression model that you can use also in the observational model here, that you can use different distributions, because sometimes you have maybe the situation, yeah, that one, so maybe a little bit kind of clustering, that you have studies, yeah, with results relatively homogeneous, and then there are some other studies with, let's say, not really completely different, but results far away from or farther away from these cluster. And then, of course, it's possible to use other distribution than the normal distribution. That's possible.
Okay, thank you, sir.
But I do not really know whether, when you are interested in and should do this meta-analysis, I always would look in the Meta 4 package, whether some of the of these results are implemented or not. So in the Meta package, it's definitely not the case, but Meta 4, maybe Wolfgang Fichtbauer has nearly implemented everything what he has found in the literature. And there are several papers on relaxing the assumption of normal distribution using some other distributions like our skewed distribution that you can do some results, but I do not know exactly whether they are implemented somewhere in R.
Sir, recently we introduced the problem in similar kind of methodology such as two one-sided and its test statistics in the context of skew normal data sets.
Okay.
Skew normal kind of case we had introduced, and on that point we are working on it.
Okay.
And we would like to extend the results in this context, in the context of meta-analysis.
Yeah, so I haven't no experience now with let's say using the skew normal. I do not think that this skew normal distribution had been used in. I only know one paper, but well, at least I remember now the the authors of this paper, but I cannot say it now immediately or at once what they did.
Okay, sir.
Thank you very much, sir. Do we have any more question here? Anybody? I think, sir, there are no more questions, so we can proceed.
Okay. So I've given you the link to the website with the other also more advanced methods for meta-analysis, and I will show you in the last, let's say, half an hour or 20 minutes of this lecture, one further application of meta-analysis. And in the last section or last lecture, I will talk about two more applied and more advanced method for meta-analysis. So now we shift a little bit to the multivariate case of meta-analysis. Up to now, we only had one outcome and do the meta-analysis, but in some studies, of course, or in some questions or studies, you have more than one outcome. And also here from the literature, there is a classical example for periodontal disease, and that you have a surgical and a non-surgical procedure, with a certain design, a split mouth design, so that each patient is its own control. And there are two outcomes, the probing depth and the attachment level. And there are 5 studies. And for each of the outcome, you have the results. So that's the mean difference between surgical and non-surgical procedure, the estimated variance of these differences. So then we have the sample covariance, and also the sample correlation. And the idea is now, of course, first, is there any difference between the surgical and non-surgical procedure with respect to the probing depth? And the same question for the attachment level. And of course, what you can do, ignoring the last 2 columns here, you could use the mean difference and the estimated variance for all studies reporting PD and for all the studies reporting AL, and you can do the meta-analysis. So, and the question is, can we, let's say, improve our statistical analysis when we use the information from both studies, and do a kind of multivariate meta-analysis. So this example is given in the literature because there is a really very, very rare situation, because we know the sample covariance, respectively the sample correlation. Usually in the published literature and the publication, you do not find this information. And I will just give you also briefly an idea on some slides what you can do in this situation. So for the multivariate meta-analysis, I will always consider now what is called here the multiple endpoints. And now the connection with this, let's say, keyword multiple endpoints and multivariate meta-analysis is now what we do with multivariate meta-analysis. At the beginning, also, we had multiple treatments using the notion of multivariate meta-analysis. But nowadays, combining multiple treatments is more or less what is called the network meta-analysis. And that is what I wanted to talk about in the last lecture. So we consider here the situation like in this example here, that we have 2 outcomes, 2 endpoints. And the question is, can we improve some sense the meta-analysis for these two outcomes when we consider both together instead of using separate univariate meta-analysis. Yeah, so and the criterion that one has is here that when we use the multivariate meta-analysis, yeah, we want to get smaller standard errors at the end of the multivariate meta-analysis of our estimates compared to the standard univariate meta-analysis. Of course, what you do is the same as in the univariate meta-analysis, again, so that it is easy, we assume always bivariate normal distribution, given in the observational model here that for each of the studies now we have two endpoints, with two effect sizes, and the within study covariance matrix given in this form. And the important thing is, of course, that you need the information of all parameters here. You may get the information of the variances or estimates of the variances, but of course the estimates of the covariance, often they are not given. And then we have the structural model given in this form, that θ1 and θ2 are now average effect sizes, and we have now let's say between study covariance matrix this capital lambda, first you can start with this general structure that you have different heterogeneity parameters for the different endpoints, and of course that they are at least here a little bit maybe correlated or not, depending what you do with the covariance here. So if theoretically the covariances here in this case and this case are 0, so then the bivariate model is identical to two separate univariate models. So the important thing is then you can also hope for a gain in the multivariate analysis, when the covariants are different from 0. And important thing, as I've already mentioned, that we need an estimate of the whole within study covariance matrix. So and what we want to do is we want to estimate these two parameters, sigma 1 and sigma 2, as well as these variant between study covariance matrix. So and for modeling the between study covariance matrix, also we can consider different approaches. We can also say that the covariance maybe are 0 and the variants are identical, or the variance for the two endpoints may be different, or we have the whole structure of a covariance matrix. I use it from here to here for the marginal model. So the marginal model for our study results looks like now the same as in the univariate case, that we have the expected vector here, the two means or true means of the two endpoints, and we have here two covariance matrices, the between study covariance matrix and the within study covariance matrix. So it's possible also to estimate these between study covariance matrix using some method of moments approaches. You do it simply for each of the parameters here. You consider different quadratic forms borrowed from the weighted regression approach, and you can easily extend an estimator. I haven't discussed in detail with you the Hedges estimator, so that the easiest part you can do, it's not so complicated like the Desimonier-Laird estimator. It just depends on the sample sizes for the weights, and you can extend the idea from the Hedges estimate to these between study covariance matrix for the estimation. Of course, we have here normality. You could use maximum likelihood approaches, restricted maximum likelihood, for instance, for estimating these capital lambda 3, no problem. So, and yeah, what is the gain? Yeah, here are some of the results. And I've used the restricted maximum likelihood approach with this complete between study variance covariance matrix. And I did the bivariate and univariate analysis. And yeah, what you see here is the result for the univariate and here for the bivariate analysis for the different parameters we are interested in. Yeah, so, and yeah, it's a little bit shifted, but near for the probing depth are the results nearly identical, I would say. And also, and that's the important thing, the standard errors for the two tests, for the two approaches are nearly identical. Yeah, so for the bivariate approach, the standard error is a little bit smaller than for the univariate, but does it really matter? Also, the estimates of the heterogeneity parameters are nearly identical. Yeah, and we can do the same for the second endpoint, the attachment level, yeah, and we would have the, yeah, let's say nearly the same result. Yeah, also, let's say a little bit disappointing that with the bivariate approach, yeah, again, the standard error of our estimate is nearly the same than the standard error in the univariate approach. And also the heterogeneity estimates, parameter estimates are nearly identical. And when you consider or calculate the between study correlation in this formula here, you will get a correlation of 0.6. So, and so that simply means that even if this between study correlation is so high or relatively large, we do not get really a gain from the bivariate approach compared to the univariate approach. What we hope is what is called borrowing of strength. Yeah, so that the idea, of course, is then in the bivariate analysis, we use the within and study correlations and hope that this maybe give us some gain. Yeah, smaller standard errors show more certainty in the estimation. Yeah, and may allow stronger conclusions for practice. Yeah, and let's say the disappointing point is a little bit that simulated complete data indicate that on average, yeah, reduction in standard error using multivariate meta-analysis over separate univariate meta-analysis is negligible for the individual pooled estimates. So that simply means in the situation we have here, yeah, all the studies report all the results, all the endpoints. Yeah, what I've calculated here is expected because of the Berkey paper. Yeah, and this complete simply means that yeah, all the studies report all the results for all the endpoints. And of course, there's now some work. Richard Riley is so the man I know who did most theoretical part for multivariate meta-analysis. And there is some, in this paper, some conclusions when we have this kind of borrowing of strength. That means that the standard errors in the multivariate model or meta-analysis are smaller than in the univariate meta-analysis. Yeah, and the formulation is here, the larger the between study correlation, the larger the differences between the within study variances, and the larger the differences between the within study variances, covariances, yeah, then we may have this borrowing of strength. Yeah, so 0.6 is not really sufficient, so it must be larger. I think in the paper it's, yeah, so the between study correlation must be around 0.9. Yeah, and of course, what does it mean here? That it relates everything to the within study variances, that there is some differences here. And recall that these estimates here are not population variances, estimates of population variance, but estimates of estimators. And that simply would mean here that you have a large difference between the within study variances when you have studies, yeah, with a large difference in the precision, so that you have studies with high precision and also studies with a low precision. If all the studies have nearly the same precision, yeah, so it doesn't work. Yeah, interpretation here for the study covariance, yeah, is not so easy, I guess. Yeah. So, however, it's not necessary that you do have complete data set. Yeah, so the general bivariate random effects model can incorporate studies, yeah, where only one of the two outcomes is known. Yeah, and of course you can extend all the methods here from bivariate to trivariate, multivariate, or something like that. Of course, there is again this usual assumption that you have when missing data, that these missing studies are missing at random. However, that in meta-analysis, of course, we only have the summary statistics, and it could also be that some of the available data are not available, not because they was not measured in the studies, but simply because of publication bias. Yeah. Or other forms, what is called here the dissemination bias. So it could be, for instance, that in 3 studies, yeah, they report the probing depth and the attachment level, the results. Yeah, in 1 study only they report the probing depth. Yeah, because this result was significant and the attachment level not, it was ignored. Yeah, and you have no idea also to see in the publication that they also measure the results for the attachment level. Yeah, and in another study, it could be vice versa, that you only have the results for the attachment level and not for the probing depth. Yeah. So, and what I did here just for demonstration is that I changed the original data set in the sense that I've deleted the results for the attachment level in the 4th and the 5th study. So assume that we only have these results here. So, and maybe this is now a situation where we have this effect of borrowing of strength, especially for the level, for the estimator of the outcome where some results are missing. Yeah. So, and that we see here in these slides, on this slide here for the probing depth. Yeah. So results for the bivariate and univariate a little bit shifted. Yeah, but the standard errors are again not so different. Now the difference is a little bit larger than in the case of, in the complete case. Yeah, the heterogeneity parameters are identical. Yeah, but what we see here, this borrowing of strength, yeah, we see it now here for the attachment level. Yeah, the standard error now in the bivariate model for the attachment level is smaller than the standard error in the univariate approach. Yeah, so the between study correlation is in the same order or same magnitude as in the case of the complete case. Yeah, so and this is, let's say, the main message first, that you have this borrowing of strength in multivariate meta-analysis when you do not have a complete data set. Some of the results should be missing, so then it's useful to use multivariate meta-analysis. Yeah, so here are just some slides with some ideas when you do not have within study correlation values. That's the usual case what you have. So one situation would be that you set them equal to 0, but of course, so this is an assumption that would be never fulfilled in these multi-treatment studies, and I think it's not a really reasonable assumption, and it's not useful in these multiple endpoint studies. So, and what you can do is just lose another description how you look at the variance covariance matrix in the random effects model. That instead of the covariance, you can also use the correlation and the standard deviation. And there are some suggestions with kind of an alternative parameterization of this covariance matrix, so that you can use some let's say overall correlation and additional variation and sampling errors to model, and I think a little bit a kind of rescue in these modeling of the multivariate approach. But the important thing is, of course, that dealing with the missing correlation values is the largest problem you have in multivariate meta-analysis. So, and at the end, of course, this multivariate meta-analysis is implemented also in meta-analysis. Let's see here. That is the R package MV meta, multivariate meta-analysis. You have all these different functions here. Just use the args function to show you the what arguments options you have here. And especially here are the methods. You have a restricted maximum likelihood, and for the between study covariance, when you use this unstructured, so that's the unstructured, that you use simply a covariance matrix in the way I've shown you with my capital lambda 3. So, and no, you do not have any exercises like in this workshop. And you will find this program multivariate MA, when you want to study a little bit about multivariate meta-analysis, on the website with this statistic.tu-dortmund.de Kerala, when you are interested in. So, and that is what I wanted to talk about multivariate meta-analysis. So again, the main message is meta-analysis, multivariate meta-analysis for multiple endpoints is only useful, not only useful, is more useful, let's say, in situations when you have, let's say, an incomplete data set. Not all the studies report all the results. If you have a complete data set, even if the between study correlation is large, like in this case here, the results of the univariate meta-analysis usually have nearly the same precision than the results of the multivariate meta-analysis. So this was my part to the what I want to give you an idea about the multivariate meta-analysis. So are there any questions, remarks?
Oh, thank you, sir. And just to inform you, Professor Bimal Sinha has also joined. And thank you for joining, Bimal sir. And if anyone has any question on multivariate meta-analysis, please feel free to unmute yourself and then ask the question. Sir, I have one small doubt till other question comes. In the example you just gave about missing value, when you had taken 2 missing observations in attachment level, we saw that the standard error of univariate analysis was much more than that of the bivariate analysis. So does the procedure of bivariate analysis in case of missing value include imputation of missing value using estimate of covariance matrix?
It's also possible, yeah. So there are some methods available. So at the beginning of my other, maybe I can just give you a switch to one of the slides here where I have the literature in the R package here. When you are interested in, so the Carpenter is the guy with the missing value imputation. He also do it with Ian White, not really for meta-analysis, also for imputation of missing values in clinical trials and so on. And in this book on meta-analysis with R, there is also at least 1 or 2 sections on how to impute missing values in meta-analysis. Yeah, so that's the only thing I could do. Yeah, so it's possible. Yeah, so Carpenter has some ideas, but of course it's not so easy to do it. Yeah, of course the thing yet is of course that maybe what can you do is, yeah, maybe that's the idea. Oops, where is it? Yeah, when you have an idea here about the kind of correlation, that's what I would say. Then maybe you can get some kind of information correlation, maybe for your effect size. Yeah, but the big question now for me would be, how do you incorporate the estimated variance? Maybe it's not so the problem that maybe you can impute a good value for the effect size estimate. Yeah, I think the bigger problem is how to impute, yeah, a value for the precision.
Yes, yes. Thank you very much, sir. Any other question? Anyone, please? I think there are no more questions, sir.
Okay.
And so we had another, each session is getting even better now, I guess. And thank you so much for another wonderful session. And we can take a break now, and we can come back at after half an hour, 3:30 p.m. by Indian Standard Time.
Okay.
Thank you, sir.
You're welcome.
Welcome back, sir. I am afraid that I was using wrong pronunciation of your name at the start. Is it, do you pronounce it as Knap or Nap?
Yeah, with a K usually in Germany, but but I know in the English spoken world it's always nap. No, so no problem. So it's you in German we say knapp. Yeah.
Yes, I'll prefer that.
Okay. So let's start with the last lecture in this workshop.
Sure, sir.
So in the last part here of our workshop, in the last lecture, I just want to discuss with you two further topics. The first one is closely related to the multivariate meta-analysis we have just discussed in the lecture before. You can also do the meta-analysis for diagnostic test accuracy studies. What you do in these test accuracy studies is that you look at sensitivity and specificity of a diagnostic tool. And the outcome in these diagnostic test accuracy studies is bivariate. Like in the example we have already discussed, now the outcomes are the sensitivity and the specificity. And the large cross-study correlation of these parameters is of interest. So there is a correlation between these two, let's say, parameters, and we want to know or learn something about it. So, and consequently, in this situation, doing a separate univariate meta-analysis for sensitivity and specificity is not the best choice. An additional point one has to remark for this test accuracy study is that heterogeneity is typically much larger in meta-analysis of these kind of studies. Because the variation between the studies is much larger, and especially how a continuous marker is dichotomized into a test classification. So here is the setup for the sensitivity and specificity. Like in the binary case, the data can be represented in a 2x2 table, so that we have the test result and the disease status. And we have the true positives that are the patients with the disease and a positive test result. We have the false positive that are the people with non-disease and a positive test result. And same we have here, people with the disease and the negative test result are the false negative, and participants with the non-disease and non-test negative test results are the true negatives. And what you can do is, given the number of diseased person and non-diseased person, they are two parameters of interest, namely the sensitivity that is the ratio of the number of true positives divided by the number of diseased patients or subjects. And specificity, yeah, so that's the number of true negative divided by the number of non-diseased in your trial. So these are the two parameters usually of interest in diagnostic test accuracy studies. And of course, you can do other things like the true positive rate, false negative rate, and so on. I will not discuss everything now what is on this slide. So the important thing here is only in the last bullet. A good diagnostic test should have both high sensitivity and specificity. Yeah, of course. Yeah, so that's good. Yeah, so there are some other measures like diagnostic odds ratio that's comparable to that what we have discussed already yesterday. Yeah, when you look here, that is the sensitivity divided by 1 minus specificity, and 1 minus sensitivity divided by specificity. Yeah, so that's simply the likelihood, let's say, of a positive or negative result. Yeah, and then you can build the ratio of these two and you will get a diagnostic odds ratio. And that's, let's say, a little bit comparable to the odds ratio we have yesterday discussed for binary data. Yeah, and again, what is the important thing here? A good diagnostic test has a large diagnostic odds ratio. Yeah, so and first remark here is directly to the R package. Meta, what you can do easily, of course, is you can calculate when you have your data sensitivity and specificity from the 2x2 table. For instance, you can use the meta prop function in the R package meta that has the advantage compared to the meta bin that you can first have the separate results for sensitivity and specificity. Yeah, the DOR, the diagnostic odds ratio, can be directly calculated, this meta bin function. Yeah, or the effect size calculation function in the R package meta4. Yeah, in meta4 it's also directly possible to calculate sensitivity and specificity. Yeah, so that's not really a big problem to do it here. Yeah, so and there is a hint to an R program where we have simply the calculation. It's not necessary to show you the program. Everything you have already seen. Yeah. So here's just a figure where you see what is going on when you have a continuous marker and you have diseased and non-diseased patients. You have a cutoff point. Yeah, what will happen when you look at the diseased patients here? You have the cutoff point. Everything right to the cutoff point are true positive. Everything left to the cutoff point are false negative. Yeah, and here you have your continuous marker for the non-disease. Everything what is left to the cutoff point are the true negative, and everything what is right to the cutoff point are the false positive. And based on these cutoff points, yeah, so there will be a correlation between the sensitivity and the specificity you have to incorporate in your meta-analysis. Yeah, and the other thing usually you need or use for diagnostic test accuracy is its receiver operating characteristic. Yeah, so based on a cutoff point, yeah, you will get 1 point of 1 minus specificity versus sensitivity. Yeah, and when you, let's say, move with your cutoff point to the left, to the right, yeah, for different cutoff points, you will get different values for the specificity and the sensitivity, yeah, and you can display it with respect to the different cutoff points, yeah, the results here in the theoretical receiver operating characteristics. Yeah, and of course, the questions then would be which cutoff point you should use, yeah, and the solution would be use the cutoff point such that the receiver operating characteristic, the ROC curve, yeah, that the value is close to the left upper corner. Yeah, so, and when you have your data, it could look like this. And it's far away from a nice, oops, ROC curve. And for different cutoff points, you have here an example where the 1 minus specificity is relatively close to 0, and the sensitivity, that's the problem here, has a relatively large variation. Yeah, with respect to the specificity, it's not a problem here with this diagnostic tool. Yeah, the problem is here the sensitivity. Yeah, and of course, what you can do is also that given the points, yeah, you can calculate confidence intervals or confidence ellipses. Yeah, and here is this kind of scatter plot with confidence regions given in these ROC space. But to be honest, you cannot see a lot different things here, and it's not so easy to find out which of these confidence regions belong to which point. But that is the data situation. Yeah? So looking again as here, it's not important to look at the confidence region. Yeah. So these are the data situation. Yeah. And now what we want to do is, first of all, to estimate an average sensitivity, specificity pair along the joint with the joint confidence region. So that's the first part. Maybe also we will try to estimate a prediction region where future pairs are expected to be found. I think I do not have slides to this point. And finally, we are estimating, trying to estimate a summary receiver operating characteristic curve. Oops. So not really surprisingly, we have two models that we can use here in this context, either a hierarchical model or a bivariate model. So the bivariate model is the model we have used in the multivariate approach, and the hierarchical model we have already seen yesterday for the random effects model. So in the case where I do not have an idea of, do not want to explain some kind of heterogeneity, so in the meter regression part we have done, when we have no covariates, then the two models are identical. Yeah, the hierarchical and the bivariate model are equivalent. And that is also only the case we will discuss here. Yeah, so it's also possible when you have a lot of heterogeneity, maybe that you can, like in the meter regression part, also to apply meter regression techniques to these diagnostic test accuracy studies, but we do not want to consider it here now. There is an R package SMADA where the bivariate model is fitted with an R function called Reitzma. He is the first author of the publication about combining the DTA studies. And the output also gives some information and estimates of parameters of the hierarchical model. Yeah, so here for ease of demonstration, I just want to consider the bivariate model where we have directly a connection to the multivariate meta-analysis we have already seen. So this is a simple model. We have the number of true positives, and we have the number of false positives. So, and we can do the following distributional assumption that the number of true positives comes from a binomial distribution, with certain number of disease person, and with the true sensitivity. And the number of false positives comes from a binomial distribution with the number of non-diseased person and 1 minus the specificity. So, and of course, in the kind of an, starting with a kind of an hierarchical model, like in the odds ratio, now we consider just the logit of these two, of these two parameters here. And we can say that the logit of sensitivity divided by 1 minus sensitivity, the logarithm of this, comes from a normal distribution with parameters theta 1 and theta 2 and these covariance structure. So instead of doing some, let's say, structural model for these two parameters directly, we do it on the logit scale, that we do these for these logit of these two parameters. So, and what we can simply do, and so that's simply the motivation only for this bivariate model, and then we simply do a combination between what's given here and given here. As you can also say it from the idea as a bivariate model. In the bivariate model, it's also kind of a binomial normal hierarchical model. So it's just important here that you will get the idea what's going on here for the modeling part. And we are interested here in sensitivity and specificity first. And you can use this MADA, and the data set is also given, or data set is given in this, or several data sets, of course, are given. And when you use the function RightSma, you will fit the model you have seen on the slides before. So, and the estimation method is a restricted maximum likelihood estimation. We will fit random effects meta-analysis. And here you will get the estimates for the parameters you will have in the model. We have, let's say, two intercepts then, and the sensitivity and the false positive rate, given from the estimates we have here for sensitivity and false positive rate as the intercept. So that's simply going from here to here. So the analysis given with the parameters are here. These are called the intercepts, and we are interested in these values here. So for the model, you have these values here, given the standard error and also the probabilities, or the p-values, sorry. So we see here that the for the false positive rate, we have here a significant result. And then you can back transform, from the model given here, for the results here, the results given here for sensitivity and specificity. So that is what you can simply do in the MADA package for combining diagnostic test accuracy studies. Yeah, and also you get here the information about the between study variances. So what you have modeled here in the way and the correlation coefficient. Yeah, so and the important thing here is of course not the ones you know that the correlation from X with X is 1. Yeah, but the correlation here between sensitivity and false positive rate is 0.6. Yeah, so and it's nearly the same as in the examples we had for the multivariate analysis. But here the important point is that we do not do the meta-analysis separately, not considering, because then it could happen that you really do not get good results for the test accuracy studies. It's always necessary that you use these bivariate or hierarchical approach. So there are some ideas of estimating a summary ROC curve. Here's a little bit some ideas given it. So I just want to show you some of the results or one result given in an R package. Yeah, I will not go through these exactly. Yeah, it's important here just that you get a kind of, let's say, impression what is going on with this diagnostic test accuracy studies. Yeah, so and you can use it simply with these plot functions and point functions here, generally that you get some ideas about the confidence regions here for the points we have calculated in our meta-analysis. And whoops, yeah. So, and finally, what we have here is that, yeah, it does not really work, let's say, in the sense that we only have this, maybe you can see this short line here, given in this part here. Of course, we do not have any data here. Yeah, so, and this solid line here is, yeah, the summary ROC curve you will get in such a problem we have seen here with the calculation given, yeah, in the output of this, what's given here in this R object, fit from the MADA object. Yeah, so just to understand what everything is going on, you have the information here already for the fit. Yeah, and what you want to do simply is here that you plot, yeah, the fit object with the options predict equals to true, yeah, and then also give your points here such that you get these confidence region and the summary ROC operating curve. So that was just what I wanted to show you, that it's still possible to do it, and it's a little bit more complicated. Yeah? So in this presentation, there are not a lot of theory. It's just that you have the idea that, let's say, techniques from multivariate meta-analysis can be also used in different situations. And one situation where you have also two different outcomes are the test accuracy or diagnostic test accuracy studies. And you can use these techniques from the bivariate meta-analysis here. And the important thing just is that, yeah, somewhere it was that we have this R package MADA that you can use. I think it was on some of the slides where I have mentioned it. Yeah, MADA, meta-analysis of diagnostic accuracy study. Yeah, so that is all what I wanted to show you here to these summary rock curve. Yeah, it was just an idea. So, and I haven't worked so much on this area, so it's not necessary, I guess, that we have here now a discussion. So in the slides you find on the website, there's also a larger partner on Bayesian approaches, but I will skip it because it's too much with this different. Yeah. So the important thing is when you do meta-analysis for the Bayesian, from a Bayesian perspective, there is this Bayes meta package. Yeah, but it's too much for the last lecture to discuss it here. So finally, I want to discuss network meta-analysis. Recall that for the multivariate meta-analysis, I said that one can use it when we have more than, or when we have 2 or more endpoints, or 3 and more treatments. But now for when we have more treatments, we do it now in not a multivariate, though it's also a multivariate approach in a certain sense. Yeah, we do it in an approach called the network meta-analysis. So, and we have here the what I've already said, network meta-analysis, also known as multiple treatment comparison, yeah, or mixed treatment comparison. So what you do here is you try to combine information from all randomized comparison among a set of treatment, yeah, for a given medical condition. Yeah, for a certain, yeah, for every disease, usually you have several different treatments. And you want to know now what is, let's say, which one is better, which one maybe is as good as the other treatment, and so on. And you have a lot of studies maybe available, and you want to combine the information. And of course, there is the idea, let's say, this kind of borrowing of strength from the multivariate meta-analysis that we can use here in the network meta-analysis, that we have all studies comparing different treatments to the same medical condition here, or for the same medical condition, to get information about how good these treatments are. Yeah, so you can say that network meta-analysis is a generalization of pairwise meta-analysis. And so that's the important thing you have to learn here just in this network meta-analysis, that we can combine direct and indirect evidence of treatment effects. Yeah, so there is a problem, of course, of heterogeneity. And additionally, here we have also maybe the problem of so-called inconsistency. And we'll discuss it a bit, I think, on the next slide. Yeah, so that simply means that direct and indirect estimates maybe give not consistent results. Yeah, and the question then is how you deal with this inconsistency. Yeah, so, and here just we again consider a weighted least squares approach. And this is implemented in the package NetMeta. Yeah, so, and there is some R code in the file, this network meta-analysis.r. And it's, yeah, because you know a little bit about using R, it's not necessary to look in this paper. There is an in this program. Yeah, so there is a data set and you can look what's going on. But at first, now I want to motivate what is meant by this network meta-analysis and the direct and indirect evidence. So let us consider two drugs, say A and B, yeah, and for a given medical condition. The drugs were shown to be effective in placebo-controlled randomized trials, and C now control that denotes placebo. But we are interested in the comparison of the two drugs and not whether they are superior to the control group. Our question is which drug is better. But we do not have, let's say, direct comparisons between A and B. We only have the comparison for A with C and B with C. So, and this may be meta-analysis estimators of the contrast-based treatment effects of A and B and C. It could be estimators just from a study. What we also can say that these are already meta-analysis estimators. And we would get an indirect estimator for A and B. When the important thing is that the treatment effects are so that it is always the difference. So that we have mean A minus mean C, or log it A minus log it C. So that's the important thing here for the indirect estimation. And then we could simply use the difference of the estimator, the effect of control cancels out, and we would have an indirect estimate of A comparing with B. And also we get a variance estimator of these indirect estimator by just considering the sum of these two estimators, assuming the independence. And what you can do is that the underlying mixed model, what we have here when you have several individual estimators of these contrast-based treatment effects, that this is equivalently can be formulated as a subgroup analysis in meta-regression. Simply that you have indicator variables for the comparison of AC and the comparison of BC. So important thing is just that you can model this simple approach. And when we have individual studies, not meta-analysis, that you have the comparing these different studies, AC, that we have KA studies comparing AC, and we have KB studies comparing BC. We can just use this kind of modeling. So, and then we would get some estimates of everything what we have here, and we can just compute the variance estimation here and here based on our meta-analysis results. So, and the question sometimes is when we only have a few studies in one of these two parts, so the estimator of the heterogeneity parameter is not so reliable. So you know when you only have 2-3 data points, so your estimate of this using the sample variance, your estimate of the variance is not so, in general, so good compared to a situation maybe where you have 20 data points. And maybe from a theoretical part, you can ask whether these two heterogeneity parameters may be equal or not, and maybe you can, instead of modeling different heterogeneity parameters, yeah, you can also model the same one. Yeah, so that's the same situation in the subgroup analysis we have briefly discussed, so that we can use either different heterogeneity parameters in the subgroups, or we assume a common heterogeneity parameter in all the subgroups. Yeah, but these problems can be easily solved using the meta-regression part. Here's a slightly more complex network. We have 4, let's say, treatments A, B, C, and D. Yeah, and it means that the line from A B to B means that there is a comparison between A and B. Yeah, we have comparisons B and C, C and D, D and A, and B and D. Yeah, but we do not have a direct comparison of A with C. And given such kind of data sets, what can be happen? Of course, we can have compute some indirect estimates for C, but you see that we have 2 possibilities. Yeah, we can go this way from A to B and B to C. Yeah, that we have comparisons AB and BC. Yeah, to get an estimate for CA. And on the other hand, we could go this way. Yeah, that we have a comparison of AD and DC, and we get an indirect estimate of AC. That's possible. Yeah, and maybe a kind of inconsistency would be when we have this way going over B, that maybe the estimate of A versus C is not in the same direction as when we go it from A to D and D to C. So that will be one problem. And the other one is, so that simply means that we have the possibility of 2 indirect estimates, and maybe they are not consistent. And the other way is with this direct and indirect comparisons. So look, for instance, at D and B. We have this indirect, we have a direct comparison of D and B. Yeah, but it's also possible to have 2 indirect comparisons of D and B. Yeah, so one possibility would be D to A and then A to B, or D to C and C to B. Yeah, and that could also be now the case that there are some kind of inconsistent results when comparing the direct comparisons with the indirect comparisons. And you should deal with these different things. Yeah. So going back to this example, what you want to do is you want to estimate first all differences between the 2 treatments, Yeah. The studies are independent. Of course, that's an important assumption we always need. Yeah, and of course, that is what I've said. The underlying effects are in some sense consistent. And formally, you can say that a network is consistent if the sum of direct treatments effects over a closed circuit is 0. In practice, consistency means that indirect evidence for the difference between any 2 treatments does not differ from the direct evidence. That is what I've explained already. Of course, extension or extent of inconsistency can you measure with the difference of the estimate from the direct and the indirect estimation process. So how do you fit or model it in this network meta-analysis? So the important thing, and do not go in all the details here now, you should have your data sets or the parameters given in this form here. Yeah, it could be in the example you have already seen that we have A, B, B, C, C, D, A, D, and B, D. Yeah, that is sufficient for the, or that would be sufficient for the modeling here. Yeah, so and then we have an X matrix in this form. Yeah, when we have several data in this form given here. So that would be A minus B. Yeah, so this would be A minus D. This would be B minus C, C minus D, and B minus D. Yeah, so, and then we have the observation given in this theta hat. Yeah, and simply by weighted least squares regression, yeah, we have our modeling. Yeah, since everything should be independent, yeah, these covariance matrix sigma is a diagonal matrix, yeah, where we have the estimates of the variances of the different estimators for the difference using here. So the yeah, so the estimator, the variance estimator of these 5 estimators. Yeah, and when you have these modeling, yeah, you can simply apply weighted least square regression, yeah, and you will get an estimate for the treatment effects here with corresponding standard errors. Yeah, and of course, the important thing just for the network meta-analysis and approach is, of course, you have a lot of more estimates, like in the example here. Yeah, what you need is the correct, let's say, model matrix, design matrix X, and you have here the diagonal matrix. So it's a little bit restricted, this modeling, that you only have studies comparing 2 treatments. Sometimes you have studies comparing 3 or 4 treatments. You can include it also in this model here. Yeah, so the only thing then you have to do, let's say when you have a study, let me see whether I have a nice example here, comparing A and B and C. Yeah, so these would be within a study, of course, correlated, that you have to model the correlation also in these covariance matrix. Of course, if you have the information about this correlation. But usually it's not really a problem to also incorporate, let's say, multi-treatment studies in this network meta-analysis. Yeah, so and here are just the formulas you may know from weighted least square regression, where you get your estimate, yeah, and where you get the covariance matrix. Yeah, and then you can have the results, yeah, for your direct estimates, and you can also look at inconsistency when you consider indirect estimates. There is something like an equivalent to Cochrane's Q, given in this form here, that you also measure, let's say, the variability. And what we do here is, as a kind of an interpretation here, is for this variability here, yeah, our estimator minimizes these quadratic form. Yeah, and on the other hand, yeah, when you're looking at the difference between the observed values and now the estimated ones, these statistic measures also the extent of heterogeneity within the network. Yeah, there is a like a correspondence to Cochrane's Q for standard pairwise meta-analysis. Yeah? So important thing here for the capital W up to now is, just go back here. Yeah, we do not have incorporated any heterogeneity parameter. So this is first the kind of a fixed effect network. Yeah, so and that's and therefore we have the correspondence here for Cochrane's Q. Yeah, so that is what I've already said with the number of multi-arm studies, and yeah, a series of two-arm studies, and you have to consider the correlation, so that I've already told you. So now the next step will be from the fixed effect model that we also want to go to the random effects model, and of course that we do here is simply that we have again, let's say a heterogeneity parameter tau square. Yeah, and the easiest way is just to assume that these heterogeneity parameter is the same for all the comparisons. Yeah, so that instead of, oops, where is it here? Instead of using only the within study variances here on the diagonal, we just add a heterogeneity parameter tau square. Yeah. So, and of course, that's also a very strict assumption that in all the comparisons we had the same heterogeneity parameter. But it first of all is for ease of computation. And of course, maybe some of the direct comparisons only we have one study. Yeah, so then it's not possible to estimate an variance just for heterogeneity, just for this comparison between the two treatments, because with one study you cannot estimate the variance. So that's the reason why we simply assume that the heterogeneity parameter is the same, let's say now in all subgroups. Yeah, and in a paper by Jackson, yeah, so there is a kind of the generalization of the Dersimonian-Laird estimator in this network meta-analysis. But of course, given the normality, yeah, you can use the restricted maximum likelihood and maximum likelihood approaches for fitting the network meta-analysis model. Yeah. So, and sometimes you also find some graphs. Just want to show you for an example here. That is the usual way you can display your network. So it's placebo here, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9 treatments. And what you see here is, yeah, they have the connections to placebo. One of the several of these active drugs, let's say, are also connected directly. These treatment is not related or not compared to placebo. Yeah, and I think that these stands for a 3-treatment study. Yeah, so that is the possibility to show how the graph is. So, and when you do the network meta-analysis, of course, it's not easy to display now all the results given the different possibilities here. And one possibility is to display the results of the treatment, the active treatments, as contrast to placebo. And that is what is done here in this forest plot. Yeah, we have here placebo, so that's just 0, so that's a comparison. Yeah, and that simply means that when we have here the name of the active treatment, it's not the effect of the active treatment, it's the effect of the active treatment compared to placebo. Yeah, and again, we have the presentation at the confidence interval with the effect size estimate here. And again, the size of the square root stands for the precision. So that in this situation here, Yeah, we have the largest value for the estimation here. Yeah, and it also has the largest precision. Yeah, so compared to placebo, this, I think it's rosy, yeah, would be the best treatment compared to placebo. Yeah. So what you can do also then is that we have this Q statistic. Let's go back to see this Q total. And you can separate something like what you could call within designs and between designs for this total heterogeneity statistic. Yeah, that's nearly the same idea in like in one-way random effects or one-way analysis of variance, where you can, the total variance can be divided in the variability between the groups and within the groups. Yeah, and the same you can do here with this heterogeneity statistic. Yeah, and then you can simply look whether they are large or not so large heterogeneities here within or between the designs. Yeah, and you can also show that these decomposition, these quadratic forms follow chi-square distribution with these corresponding degrees of freedom. And these are the p-values, so that you can say in this example here, there's a large variability within the designs and also between the designs. Yeah. So, and this is what's going on in the network meta-analysis. So, and here I would like to stop with the network meta-analysis just to give you an idea. There are some net heat plots, but I think it's too much or too difficult to explain now these net heat plots just with these few slides. Yeah, so it's a kind of correspondence between the correlation of these values or active treatments here, and which has more effect, which one has more effect in the network than other, and then other comparisons. So a little bit text, maybe when you're interested in, you can look in it. So that was the two ideas I just wanted to give you in the last lecture. So I have here some final slides. I will also show you the final slides, but maybe now, maybe there are some questions or remarks, especially to the network meta-analysis. I just wanted to give you an idea about network meta-analysis here. Usually you can do one-day workshop on network meta-analysis. But are there any questions for this part, for the network meta-analysis?
If anyone has question, please unmute yourself and ask. I guess
Yes.
there are. Yeah. There's no question for this part, I guess.
Yeah.
Yeah.
Okay, so just as a reminder, so the important part simply is to do the modeling here. Yeah, so the it is important to find the correct X matrix. Of course, the software is doing it, and then everything is the same, let's say, like in weighted least squares regression. Yeah, so that's what is the important part here. Okay, when there are no questions, I will conclude with some slides to give you an overview what's still you can find on meta-analysis. When you go to want to know what is given also in R, you can go to the CRUN task view for meta-analysis on this website, and you get several topics. Yeah, so the univariate meta-analysis, multivariate meta-analysis, these of diagnostic studies, meta-regression, individual participant data, network meta-analysis, and a little bit other. Yeah, so more or less in this workshop, we have discussed most of the first 6 topics. And simply you can find here additional information, especially in the sense which R package you can use when you want to do univariate, multivariate meta-analysis, and so on. Yeah, so for the univariate meta-analysis, we have discussed a little bit more in detail meta and meta 4. Of course, there are a lot of other univariate meta-analysis, also depending on the area where the authors of the R packages work. Several areas of applications, for instance, in psychology, they have other problems than people working in meta-analysis of clinical trials. But that is a nice overview to these topics you can find on the website, yeah, CRUN task queue. Yeah, so there is some what I have here, some bullets for the univariate meta-analysis, and so there are some topics here, and especially then when you have, for instance, to prepare something for the meta-analysis are packages, some additional packages, Meta Plus and Meta Plus and MetaLec. Yeah, I will say something to Meta Plus because it corresponds to the question we had in the last lecture, and also some other situations. Yeah, there's also for p-values, so unobserved studies. Yeah, so there is a little bit in this R package, Dr. Leo, so I think it was your question with this missing data. Yeah, so there's also package MetaSense where you can find some of the information. So, and this is maybe, I think the other ones are not so important, maybe in my last slide here in the lecture, yeah, corresponding to the question we had for this Q normal. And now I have found this slide here at the end. In the meta-analysis part, there is not really something about skewed distributions here, especially not implemented in these R package here. There is this R package Meta Plus, which said that is R package for robust meta-analysis and meta-regression. And there is some references given here. And implemented as instead of the normal distribution, when you use a T distribution, yeah, so extreme case T distribution is 1 degree of freedom, so that at least you have a little bit more or a heavier tails in this situation. I thought that Baker and Jackson, they had in this paper, in their paper, also something about skewed distribution, but maybe it's not implemented here in this R package Meta Plus. Yeah, and the other thing is what you can find here in this R package, yeah, that you try to find or can use some kind of mixtures of normals. That is a situation I've already also discussed a little bit or mentioned in the last section, when you maybe have some clusters, so that you can find some, let's say, groups of studies which are more homogeneous on one part, and then on the other part, maybe also some groups. Yeah, so maybe that the mixture of normals would be also a possible idea how you can do the meta-analysis. Yeah? And of course, there are a lot of extensions you can find, like also in the Metallic and other papers. Yeah, just have here on my slides only a few. Yeah, but when you go on the website here, you will find a lot of packages for meta-analysis. So last time I found an overview paper and they checked all the R packages for meta-analysis. And I think at that time, it was 2 or 3 years ago, there were at least 60 packages, R packages for meta-analysis. So when you do meta-analysis, you have a lot of R packages available, which you can use. So that would be the end of my presentation here in this workshop. I hope you have got an idea about everything you can do in meta-analysis, and maybe when you want to do a meta-analysis, now that you will be able to do the basics and maybe also some of the advanced methods for meta-analysis. So thank you for attending this workshop.
Thank you so much, sir. I'm sure everyone will agree when I say that in just 2 days, we have gained a lot from your lectures. And just before we move on to the closing session, like I have some general questions. If you allow, I would like to ask.
Yeah, sure.
Okay. So my question was like, suppose we have estimate of any effect from different studies where very different methods have been used for estimating the effect. Like these are not, suppose these are like survival rates coming from different studies and different models. In some model, parametric models have been used for estimation, including say censorship, while in some models, say only Kaplan methods have been used. So can we use all these studies for meta-analysis? Can we use all of them together?
So the easiest answer now I can give is we need another workshop. Of course, given the problem now you have, you cannot directly use the methods I have presented. Of course, that is the situation that you have to do some kind of data preparation before, and it's not easy. So there are several solutions, or not really solutions, but proposals how to deal with it. Yeah, for instance, when you only have the Kaplan-Meier estimators, yeah, so some people really developed something. You have only the survival, the Kaplan-Meier curve in the publication. Yeah, that they try to extract the information, for instance, for the log rank test or something like that. Yeah, so maybe that you can try to measure in some sense the hazard ratio. Yeah, so there are a lot of things in this area or in this direction when you have different, let's say, scales or different methods. It's not easy to do this, but they are in certain areas, there are some proposals. Another proposal maybe that fits a little bit to the diagnostic accuracy study, especially in psychology, sometimes they have continuous variables and they use the standardized mean difference. And in other studies, they use the cutoff point and their odds ratio is reported. Yeah, and I think when I go here to the slide, when you look at this point here, this preparing for meta-analysis, yeah, under this topic in the univariate meta-analysis, you find some packages also which do a kind of transformation, for instance, from the standardized mean difference to the odds ratio. Also, there's a kind of correlation. There is a correlation to the correlation coefficient. Yeah, so sometimes you do have to do some preparation before. And on the other hand, maybe also maybe related an answer to the general question. For instance, in epidemiology, you maybe have different models, and you have different models used for estimating the treatment effect. And of course, you have, let's say, used a different set of confounders, maybe. Yeah, so then, of course, I also had one paper on this epidemiological application, and we had this problem. And then, of course, you have to do a trick. Yeah, simply that you have say that you can combine all the treatment effect estimates from the different models. Maybe if you assume that the model in each study is the best, that you have considered all important confounders in the study, and maybe when the other study do not have this confounder, maybe that was also not important for this study. So it's it's sometimes I think in English is comparing apples and oranges. So sometimes a criticism also of meta-analysis when you pool too many things together. Right. And the question simply is sometimes is it really how to can we pool or to pool or not to pool for the meta-analysis? But that's a general problem in the meta-analysis when you have, let's say, different approaches for different, let's say, applications. Maybe also combining tests, whether you have a parametric or non-parametric tests. There are a lot of problems, and also there is a lot of, let's say, room for having new ideas.
Exactly. Thank you so much, sir. So I would ask if anyone has any other question or would like to share their experience or say something to Professor Geeta Knapp. Please, you are welcome. You can unmute yourself. Lots of words of appreciation are being posted on the chat group for you, sir, from the participants. If anyone wants to share their experience or have any doubt, any question, you can ask right now. Okay, I guess people are using the chat more often now. And so before we proceed, sir, I would invite Parmeet, and he wants to give an overview of the diversified participation in this workshop. Hi, Parmeet, over to you.
Yeah, good evening, sir, and good evening, all the participants. It was a very wonderful session with sir. We received overwhelming response from different parts of India and from even abroad. So this happened within hours when we released the leaflet. So it was very difficult for us to stop or to filter. So what we did was on the day one itself in the night, we had to stop because the registrations were 3 times whatever we have expected. So sorry for those we could not accommodate. Maybe in future we will try to give them also a chance. So we have PG students, research scholars, faculty members, scientists, and statisticians from various communities, like from private companies and government institutions. So the audience were of various regions and institutions. So thank you, sir, for the great sessions, and thank you to the participants also. Over to Vishal, sir.
Thank you, Parmeet. Now, I would request Professor Gurpreet Gaur, ma'am, please say a few words.
Thank you, Vishal. First of all, I would like to thank Professor Bimal Sinha, sir, who was in fact instrumental in initiating this workshop. Thanks a lot, Professor Bimal Sinha, sir. And I also want to, in fact, I don't have words to express my gratitude to Professor Gaidonet, who shared his knowledge with us on statistical meta-analysis using R. This workshop was full of knowledge and gave deep insight into the topic with interesting examples and so many applications which we can't even think of. He has given so many applications. Thank you so much, sir. I'm sure the precious knowledge shared by Professor Neff about statistical meta-analysis will definitely help us in our future research work. I would also like to thank all those who have directly or indirectly supported us in the organization of this workshop. In the end, thanks to all the participants for their patience and interest in learning. Thanks to all of you. Special thanks to Professor Bimal Sinha and Professor Gaido Net. Thank you. Thanks to all of you.
Yeah, thank you for the kind words. I really appreciate this workshop.
Thank you, sir. And actually, this is like blessing in disguise. Like we are thinking about having online lectures now, because earlier we preferred physical workshop. It has obviously we miss a lot of things about physical workshops. There we can have better interaction and interaction beyond the topics also. So we do miss that. Hopefully, maybe we can have sometime later physical workshop also. And thank you so much, sir. And Professor Bimal Sinha, sir, you are here. If you want to share some words with us, you are always a motivation for all of us. I think maybe as on offline now. Yeah.
Yeah, where's unmute? Mute, muted, still muted.
Yeah, it is possible he's on offline because of some reasons. So. Okay, so I think we have reached here before time, and
Vishal, you can share the appreciations from the participants to with Professor Net.
yes, ma'am, definitely. Lots of appreciation messages are coming for you, sir, and all of them think that the workshop was really motivating and very informative, and very immensely enriching also. Actually, I would say it personally, which I think everyone will agree with, like 2 days before I was a stranger to statistical meta-analysis, but now just 6 sessions with you, and I feel like I should also think about working at least in the applied field of meta-analysis. And so that is the kind of confidence I have gained from attending a workshop, which is like 2 days, achieving something in 2 days. That is only possible because you have explained everything so clearly, using the flow of explanation was so good, using examples. You focused on the purpose, and then the theory behind it, and then how to implement it in R. So everything was there. It was a very comprehensive workshop. So thank you very much.
Yeah, you are welcome, and thank you for the nice words, and also to the participants for that they have, let's say, a little bit enjoyed and learned something from this workshop. Thank you.
Thank you, sir. So with permission from Professor Gurpreet Bro, if should we now call up the session?
Yes, thanks to all of you. Special thanks to Professor Knapp. We will try to meet again if your time schedule permit.
Yes.
Okay.
Thank you.
Thank
So,
you.
Okay, so that is the formal end of the session then. And goodbye, everyone.
Okay. Goodbye.
Goodbye to all of you.